A few years ago, scientists pointed their telescopes at a distant star and found something nobody expected. A planet so hot that it makes our sun look cold next to it. The temperature on the surface of this world reaches more than 4,000 degrees, enough to melt any metal we know. Even iron and titanium turn into smoke there. This extreme heat happens because the planet is stuck to its star, orbiting so close that an entire year lasts only a few hours. But here is what left scientists confused. How can a planet exist in such terrible conditions without simply evaporating? Get ready to fall asleep while listening to this video and travel to this impossible world. Subscribe to the channel. Leave your like and comment where in the world you are watching from. Get comfortable and relax. Let's begin. Sometimes the most groundbreaking discoveries in astronomy come completely by chance, not from careful planning. Imagine looking for a tiny, Earth-like world and instead stumbling upon a blazing inferno of a planet that defies all logic. This is exactly what happened when scientists were sifting through data from a survey designed to find habitable exoplanets. They were focused on stars that might host planets with conditions similar to our own, using the transit method, which involves monitoring the brightness of stars over time. When a planet passes in front of its star, it causes a slight dimming, and by measuring these dips, astronomers can detect the planet's presence. But in this case, the data showed something bizarre. A minuscule and incredibly rapid decrease in brightness that lasted for a very short period. This signal was so faint and quick that it almost went unnoticed, buried in the noise of countless other measurements. Initially, the team thought it might be an instrument error or perhaps a flaw in the data processing algorithm. However, upon closer inspection, they realized this anomaly was consistent and repeatable, pointing to the existence of a real celestial body. The transit dip was much smaller than those caused by Earth-sized planets, and the speed of the transit indicated an orbital period measured in just hours, not days or years. This was unprecedented. No known planet orbited its star so quickly. To confirm their findings, they turned to another powerful technique called the radial velocity method. This method relies on measuring the star's spectrum to detect tiny wobbles caused by the gravitational pull of an orbiting planet. As the planet moves around the star, it tugs the star back and forth, shifting the light wavelengths in a predictable pattern. When they applied this method to the same star, they detected a clear wobble that matched the timing of the transit signals. The combination of transit and radial velocity data allowed them to calculate the planet's mass and orbital characteristics. They found that this world was a gas giant with a mass several times that of Jupiter, yet it was orbiting so close to its star that it completed a full revolution in a matter of hours. The discovery was shocking because it challenged everything scientists thought they knew about planet formation. According to established theories, gas giants like Jupiter form in the cold, outer regions of a planetary system where ice and gas can accumulate. A planet this massive should not exist so close to its star. The environment is too hot and violent for such a world to form in place. This led to the immediate hypothesis that the planet must have migrated inward from a farther orbit. But how it managed to stop before being consumed by the star became a major puzzle. The accidental nature of this find cannot be overstated. The researchers were not searching for such an extreme object, but their openness to anomalies allowed them to recognize its significance. The survey involved automated telescopes that continuously monitor large patches of the sky, collecting vast amounts of data on star brightness. These telescopes are part of networks like KELT, which stands for Kilodegree Extremely Little Telescope, designed to detect transits of planets around bright stars. When the software flagged this unusual event, it required human intuition to pursue it further. The scientists had to rule out other explanations, such as binary star systems or stellar activity, which can mimic planetary signals. They conducted follow-up observations with other instruments, including high-precision spectrometers on larger telescopes, to gather more data. Each new observation reinforced the initial conclusion. They had found a planet unlike any other. The publication of this discovery sparked excitement and curiosity across the astronomical community. It was quickly recognized as the hottest planet ever discovered, with equilibrium temperatures surpassing those of some stars. The mere existence of such a world forced theorists to revise their models of planetary migration and evolution. How could a gas giant survive so close to a star without being torn apart? The intense radiation and gravitational forces should have stripped away its atmosphere or caused it to spiral into the star. Yet here it was, a testament to the diversity and resilience of planetary systems. This finding also highlighted the importance of survey missions that cast a wide net, as they can uncover rare and unexpected phenomena. The team's perseverance in investigating a subtle signal paid off, leading to a major advancement in exoplanet science. It reminded everyone that in the vastness of space, there are always surprises waiting to be found, often in the places we least expect. The planet was given a technical designation, but it became popularly known as an ultra-hot Jupiter, a class of planets defined by their extreme temperatures and close orbits. The discovery process involved collaboration among multiple observatories and research institutions, showcasing the collective effort modern astronomy requires. Data from space telescopes like Hubble and later James Webb would eventually provide deeper insights. But the initial revelation came from ground-based observations. This accidental discovery not only added a new record holder to the exoplanet catalogue, but also opened up new research avenues into the physics of extreme environments. It showed that our understanding of the cosmos is continually evolving, and each unexpected find pushes the boundaries of knowledge. So, the next time you hear about a chance discovery in science, remember that it often leads to the most profound lessons about the universe we inhabit. So now that we have this accidentally discovered planet, what exactly are we dealing with? Let us paint a picture of this truly extreme world, starting with its official, albeit dry, designation, DOT. While it might have a catalogue name like KELT-9b, its true identity is far more dramatic than any string of letters and numbers could ever convey. The most immediate and shocking characteristic is its sheer heat. The equilibrium temperature here is not just hot, it is stellar, routinely exceeding 4,000 degrees Celsius. That is not a typo. This planet is so hot that its temperature rivals that of the coolest stars in the universe, the red dwarfs. You are essentially looking at a gas giant that is as hot as a star, which immediately redefines what we consider possible for a planetary body. It falls squarely into the category of what astronomers call an ultra-hot Jupiter. This means it is a gas giant, similar in basic composition to our own Jupiter, but with a mass several times greater. However, that immense mass is not packed into a dense ball. The intense, relentless heat from its nearby star has caused the planet's atmosphere to puff up dramatically, like a cosmic balloon being heated. This inflation results in a planet that is physically much larger than Jupiter but has a surprisingly low overall density. It is a vast, bloated world, tenuous in its outer layers. But do not let that fool you into thinking it is harmless. The conditions here are utterly lethal. The gravitational pull is still immense due to its great mass, and the atmospheric physics are something out of a nightmare. This proximity to its stellar host has another critical consequence: tidal locking. Just like our moon always shows the same face to Earth, This planet is locked in a gravitational embrace with its star, meaning one hemisphere is in perpetual, blistering daylight while the other is trapped in an eternal, though still scorching, night. This setup creates the most radical contrast imaginable between the two sides of the same world. The day side is being bombarded by the full, unfiltered fury of the star's radiation, cooking it to those incredible temperatures. The night side, while shielded from direct irradiation, is still incredibly hot by any normal standard, but the temperature difference between the two hemispheres is thousands of degrees. This colossal gradient does not just sit there, it drives a system of hyperviolent weather. Imagine winds that are not just strong, but supersonic, screaming across the planet as they attempt to redistribute the insane heat imbalance. The entire atmosphere is in a constant, turbulent state, a maelstrom of forces acting on a scale we can barely model. The chemistry, or more accurately, DOT, the lack of conventional chemistry, is another defining trait. At these temperatures on the day side, molecules cannot exist. Any complex arrangement of atoms, like water vapor or methane, is instantly torn apart by the immense radiative energy in a process called photodissociation. What remains is a soup of individual atoms and ions, a plasma-like state where elements like iron and titanium float around not in solid or liquid form, but as gaseous and ionic constituents. This leads to the bizarre possibility of metal clouds and even rain made of liquid iron, a concept that sounds like science fiction but is a genuine theoretical prediction for such environments. The planet's size, while large, is also a function of its heat. If it were somehow magically moved to a colder orbit, it would likely shrink considerably as its atmosphere cooled and contracted. But here, in its natural inferno, it maintains its inflated stature. The low density means that if you could find a way to stand on a hypothetical solid surface, which you cannot as it is a gas giant, the gravity might feel different than on a more compact world, but the environmental hazards would vaporize you instantly regardless. The radiation environment is another key feature. The star it orbits is not a gentle, yellow sun like ours. It is a hot, blue dot, type A or B star, pumping out enormous amounts of high-energy ultraviolet and X-ray radiation. This radiation does not just heat the planet, it actively batters and strips away its outer atmosphere. Scientists believe the planet is slowly evaporating, losing mass over time as the stellar wind and radiation pressure blow the atmospheric gases into space, potentially creating a giant, comet-like tail. This evaporation rate, however, is slow enough that the planet will persist for millions of years, a testament to its substantial initial mass. The permanent day side is the hottest point, but the heat is not evenly distributed. Models suggest that the hottest spot might not be directly at the substellar point, the spot facing the star most directly, but could be shifted by those powerful global winds, carrying heat eastward or westward. This creates a complex temperature map that astronomers are keen to study to understand fluid dynamics in such an extreme regime. On the flip side, the permanent night side offers a slightly, and we use that term loosely, more moderate environment. Here, temperatures might plummet to a mere 1,500 to 2,000 degrees Celsius, allowing for some fascinating and exotic physics. In this relative coolness, some of those vaporized metals from the day side could actually condense, forming clouds of liquid iron or titanium oxide droplets. But this respite is temporary and violent. Any material that condenses is soon caught in the supersonic winds and dragged back to the day side, where it is flash vaporized once again, completing a terrifying meteorological cycle. The planet's composition is like a direct sample of what you would normally find deep inside a rocky world's core. elements that are locked in minerals on Earth, like titanium, vanadium, DOT, and rare earth elements, are floating freely in the atmosphere here. Detecting these requires sophisticated spectroscopy, analysing the starlight that filters through the planet's atmospheric rim during transit. Each element leaves a unique fingerprint in the light, allowing us to decode this exotic periodic table in plasma form. The presence of neutral iron, ionized iron, and molecules like titanium oxide, only stable at high temperatures, provides crucial data for physicists. Studying this world is not just about understanding one bizarre planet. It is about stress testing our models of atmospheric physics, chemistry, and planetary evolution under conditions we cannot recreate in any lab. The extreme nature of this Jupiter also tells us about the limits of planetary survival. How close can a gas giant get to its star before it is completely torn apart? What are the ultimate processes that dictate its lifespan? This world sits right on the edge, providing a natural laboratory for these questions. Its very existence challenges our definitions and forces us to expand our understanding. When we talk about weather, we think of water clouds and rain on Earth. Here, weather involves metallic vapor, supersonic shocks, and global heat redistribution on an unimaginable scale. The dynamics are so intense that they might even generate a magnetic field through internal processes, though measuring that from such a distance is a monumental challenge. The planet's orbit is incredibly tight, completing a full circle around its star in just hours. This means a year on this world passes in less than a single Earth day. The velocity required to maintain such an orbit is staggering, hundreds of thousands of kilometers per hour. This speed, combined with the tidal forces, keeps the planet stretched and likely contributes to internal heating through friction, adding another source of energy to an already overpowered system. In many ways, this world is a transitional object, blurring the line between a planet and a star. It is not massive enough to ignite fusion in its core and become a star itself, but its atmospheric conditions are stellar in nature. This makes it a unique touchstone for understanding the lower end of the stellar mass spectrum and the upper end of the planetary one. As we continue to observe it with powerful telescopes like James Webb, we are unraveling more of its secrets, each data point revealing a deeper layer of complexity in this portrait of an extreme world. It serves as a constant reminder that the universe is far more creative and violent than we often imagine, capable of producing worlds that defy our simplest categorizations and push the boundaries of physical laws as we know them. To truly grasp the nature of that bizarre, ultra-hot Jupiter we just described, you absolutely must understand the cosmic engine powering it all, the host star, ... This isn't a gentle, yellow sun like our own. It's a completely different class of beast, a type A or B star that operates on a level of ferocity that makes our sun seem placid and tame. These stars are the real powerhouses of the galaxy, significantly hotter, larger, and more massive than the sun. Their immense mass means the pressure and temperature at their cores are far greater, causing them to burn through their nuclear fuel, hydrogen, ... at a frantic, almost wasteful rate. This furious rate of fusion generates an unbelievable output of energy, but not just in the form of visible light we see. The real story lies in the high-energy radiation this star pumps out into its system. We are talking about colossal amounts of ultraviolet radiation and X-rays, a constant, invisible barrage that is far more aggressive than anything any planet in our solar system ever experiences. The surface temperature of this star is staggering, routinely exceeding 10,000 Kelvin. For context, Our sun's surface is around 5,800 Kelvin, so this star is literally more than twice as hot. That intense heat translates directly into the colour of the light it emits. It's not yellow or orange, but a brilliant, searing blue-white. This blue-white glow is a direct visual indicator of the tremendous thermal energy being released. Now, this is the crucial part for understanding the planet's extreme heat. While the planet's close proximity is a major factor, it's this specific type of radiation from this specific kind of star that creates the inferno. The proximity gets the planet close to the fire. But the star's nature means it's not just a campfire. It's a blast furnace emitting a blowtorch of high-energy photons. The ultraviolet and X-ray radiation carry so much energy per photon that they don't just warm the planet's atmosphere. They violently interact with it. These high-energy photons have enough power to break apart molecules in a process called photodissociation, which is why the planet's day side has no water, methane, DOT, or any complex molecules. They are torn apart the instant they try to form. Furthermore, this radiation doesn't just stop at the upper atmosphere. The X-rays, in particular, can penetrate and heat the outer atmospheric layers to tens of thousands of degrees, creating a massive, puffed-up thermosphere that essentially boils off into space. This is a key mechanism behind the planet's observed evaporation. So, the heating is a multi-layered process. Simple radiative heating from the star's visible light and infrared, plus intense heating from the photodissociation process, which converts radiative energy into thermal energy, and then the direct heating of the upper atmosphere by X-rays. It's a triple whammy that simple proximity to a cooler star could never achieve. But the star's influence doesn't stop with radiation. Stars like these are also known for their powerful stellar winds. The solar wind from our sun is a stream of charged particles, but from a hot type A or B star, the wind is far more intense and faster. This is because the high temperature of the star's corona, its outer atmosphere, allows the plasma to escape the star's gravity much more easily, resulting in a supersonic flow of particles racing outward. This relentless stellar wind slams directly into the planet's atmosphere. Since the planet is so close, it's essentially orbiting within the star's extended corona, that region of superheated plasma. This constant collision compresses the planet's atmosphere on the day side and likely helps strip it away, contributing to the comet-like tail of evaporating material. Then there's the magnetic component. Massive, hot stars often possess strong magnetic fields. While their magnetic fields can be structured differently than those of cooler stars, they are still potent forces that can interact with any planetary magnetic field. If the planet has a magnetic field of its own, which is a topic of intense speculation, the interaction between the star's magnetic field and the planet's could be dramatic. This interaction could funnel charged particles along magnetic field lines onto the planet's poles, generating immense auroras that would be billions of times more powerful than Earth's northern lights, and potentially dumping even more energy into the atmosphere, creating localized hotspots of extreme heating. This complex magnetic dance is another way the star transfers energy to the planet beyond pure radiation. Now, let's talk about the life cycle, because that adds another layer of drama to this system. A star like this lives fast and dies young. While our sun has a total lifespan of about 10 billion years, a massive type A or B star burns through its fuel so rapidly that its entire life, from birth to death, might only last a few 100 million years. That's a mere blink in cosmic time. This short, brilliant life has profound implications for any planets in the system, especially one orbiting so close. The star is destined to evolve off the main sequence relatively soon, in astronomical terms. It will exhaust the hydrogen in its core and begin to swell into a red giant, or perhaps transition through other evolutionary stages like becoming a subgiant. As it expands, its outer layers will cool and its radius will increase dramatically. For a planet orbiting at a distance measured in a fraction of 1 astronomical unit, the outcome is inevitable and grim. The expanding star will engulf the planet. Long before the final act, the star's increasing luminosity as it ages will pump even more energy into the planet, likely accelerating the atmospheric evaporation and heating it to even more ludicrous temperatures. The planet's fate is sealed. It will be vaporized, completely destroyed and assimilated into the star's outer layers. This impending doom makes the system a fascinating time capsule. We are essentially observing a short-lived, violent phase in a planetary system's history, a phase that our own solar system never went through. Studying this star-planet pair gives us a preview of the final stages for many hot Jupiter systems. The intense radiation environment also affects the possibility of other planets or moons in the system. Any rocky body orbiting within a significant distance would be sterilized and melted, its surface scoured clean by the relentless UV and X-rays. The circumstellar region where planet formation typically occurs might be truncated or altered because the protoplanetary disk from which this system formed would have been much hotter, affecting the types of materials that could condense into planets closer in. The chemistry of the disk would have been different, with ices and volatile compounds unable to survive near the star. This might explain why such a massive planet likely formed farther out and then migrated inward, as forming in place so close to such a luminous young star would have been incredibly difficult. The star's high temperature also affects how we observe the planet. The contrast between the star's brightness and the planet's own emitted light is less extreme in the infrared than it would be for a cooler star, making it slightly easier for telescopes like the James Webb to detect the heat signature from the planet's day side. The star's spectrum, dominated by blue and ultraviolet light, provides a bright background against which we can study the absorption signatures of elements in the planet's atmosphere during transit. So, in every way, the character of the host star defines the character of the planet. It is the ultimate puppet master, dictating the temperature, driving the atmospheric escape, influencing the chemistry, and ultimately setting the expiration date for its close-orbiting companion. Without this specific type of stellar furnace, the planet simply would not be the record-breaking, hellish world that it is. It's a reminder that planets cannot be understood in isolation. They are products of their stellar environment, and in this case, the environment is the most extreme imaginable. The study of this system forces astronomers to consider stellar physics and planetary science as an intertwined discipline, where the properties of the star are the first and most critical piece of the puzzle in understanding the bizarre worlds that might be orbiting it. As we discover more of these ultra-hot Jupiters, we are finding that they are almost exclusively around these hotter, more massive stars, confirming the intimate and destructive relationship between a star's nature and the ultimate fate of its innermost planets. This knowledge is crucial as we search for habitable worlds around other stars, teaching us to look not just at the planet's position, but intently at the star it calls home. Now, having understood the sheer power of the host star, let's zoom in on the planet's mind-bending trajectory. Because its orbit is not just close, it's ludicrously, almost impossibly tight. This is where the root cause of all that extreme weather and heat truly lies. Imagine a year on Earth, with its 4 seasons, its slow journey around the sun. Now, compress that entire annual cycle into a span of time shorter than a single Earth day. That is the reality for this world, its orbital period. the time it takes to complete one full circle around its star, is measured in just hours. This isn't a gentle elliptical path. It's a frantic, screamingly fast dash that keeps the planet perpetually on the brink. The distance involved is almost incomprehensibly small. In our solar system, we measure distances in astronomical units, where 1 AU is the average distance from Earth to the Sun. This planet orbits at a distance that is a tiny fraction of that dot, often calculated to be less than 0.02 AU. To put that into perspective, Mercury, the innermost planet in our system, orbits at about 0.39 astronomical units. This world is well over 10 times closer to its star than Mercury is to our Sun. At such an intimate distance, the gravitational forces at play are absolutely immense. The star's gravity doesn't just gently pull on the planet, it dominates it completely, leading to a phenomenon known as tidal locking. You see this with our moon, which always shows the same face to Earth. This planet is similarly locked, forced to present one hemisphere permanently towards the stellar inferno and the other forever turned away into the relative darkness. This tidal locking is a direct consequence of the gravitational gradient. The star's pull is so strong on the near side compared to the far side that it has effectively stretched the planet and halted its rotation relative to the star. This fundamental configuration is what creates the radical dichotomy between the permanent day side and the permanent night side, setting the stage for those supersonic winds that try to balance the insane temperature difference. But the orbit's extremity goes even further. This planet doesn't just orbit near its star, it orbits within what we would consider the star's own extended atmosphere. The region is called the stellar corona, a halo of superheated plasma that we normally associate with the star itself. So, this world is literally flying through a sea of million-degree gas, adding another layer of environmental violence. The stellar wind, a constant stream of charged particles flowing from the star, hits the planet's atmosphere at full force, contributing significantly to the atmospheric erosion and the potential formation of a giant, comet-like tail. The orbital velocity required to maintain such a tight path without falling directly into the star is nothing short of colossal. We are talking about speeds of hundreds of thousands of kilometers per hour. This incredible speed means the planet is essentially in a constant state of free fall, but moving so sideways that it keeps missing the star. It's a delicate, high-speed balancing act. The centripetal force needed to keep it in this circular path is provided entirely by the star's gravitational pull. If the planet were moving any slower, it would spiral inward and be consumed. This breakneck pace also means that from the planet's perspective, if it had one, the sky would be dominated by a single, enormous, and terrifying object, the star, It would not appear as a small disk, but as a vast, blazing wall of fire stretching across a significant portion of the heavens. The transitions between what we would call day and night don't exist. The conditions are permanently fixed on each hemisphere. The gravitational forces involved in this close dance also generate significant internal heating within the planet through tidal friction. As the star's gravity pulls on the planet, it flexes the planet's interior, much like the moon's gravity flexes the Earth's oceans to create tides. This constant flexing and squeezing generates heat through friction, adding another internal source of energy to a world that is already being cooked from the outside. This internal heating might contribute to the planet's inflated size and could even play a role in sustaining any potential magnetic field, though that remains a subject of intense study. The orbit itself is likely very stable over short timescales, but on cosmic timescales, it might be decaying. The same tidal forces that lock the planet could could also be slowly sapping its orbital energy, causing a very gradual spiral inward towards eventual destruction. This process is subtle and might take millions of years, but it underscores the precariousness of the planet's existence. It is living on borrowed time in a supremely hostile neighborhood. The discovery of orbits like this forced astronomers to completely rethink how planetary systems form and evolve. Traditional models suggested that gas giants form in the cold, outer regions of a protoplanetary disk. A planet this massive, so close to its star, presented a huge puzzle. The leading theory is that it formed much farther out, in a more temperate zone, and then migrated inward over time. This migration could have been driven by interactions with the gaseous disk early in the system's history, or by gravitational encounters with other planets. Somehow, this migration process stopped before the planet was swallowed whole, leaving it in this astonishingly close orbit. Understanding this braking mechanism is a key area of research. The planet's orbit also makes it a prime target for certain observation techniques. The transit method, where we detect a planet by the dip in starlight as it passes in front, works exceptionally well here because the transits are frequent. With an orbital period of just hours, astronomers can observe multiple transits in a single night, gathering a wealth of data quickly. The short period also means the signal is strong and repetitive, making it easier to confirm and study. Furthermore, the planet's velocity, measured via the radial velocity method, produces a very clear and large wobble in the star, making its detection and mass measurement more straightforward than for slower, more distant planets. However, the extreme environment poses challenges too. The proximity to the star means that during a transit, only a very thin sliver of the planet's atmosphere is backlit by the star. And separating that signal from the star's own intense light requires incredibly precise instruments. The planet's own emitted heat, especially from the day side, can also be studied through secondary eclipse observations, where we measure the drop in infrared light when the planet passes behind the star. This allows scientists to map the temperature distribution between the day and night sides. The orbital configuration means these secondary eclipses also happen very frequently, providing regular opportunities for data collection. In essence, this grazing orbit is the engine of the entire system's drama. It is the reason the temperatures are so high, the weather so violent, and the chemistry so exotic. It defines the planet's shape, its rotation, and its ultimate fate. Without this specific orbital dynamic, this world would be just another gas giant. But because of this frantic, close-in dance, it becomes a laboratory for extreme physics, pushing our understanding of what is possible in the universe. It teaches us that planetary systems can be arranged in ways we never imagined, with worlds occupying niches so extreme they blur the line between planet and star. As we continue to search for exoplanets, finding more of these ultra-short period worlds helps us understand the limits of orbital stability and the diverse outcomes of planetary migration. Each one is a data point in a larger story about how planetary systems are born, evolve, and sometimes create these incredible, hellish marvels. So, we have this planet locked in a death spiral orbit. But what actually pumps the heat up to such stellar levels? It is not just about being close to the fire. It is about the specific ways that fire delivers its energy, turning the entire world into a complex thermal engine. Proximity is the obvious starting point, but the heating mechanism here is a layered, multifaceted process that involves everything from high-energy photons to internal gravitational friction. Think of it this way: if you just had simple radiative heat from a star like our Sun, even at that distance, it would be incredibly hot. but it would not reach the 4,000 degrees Celsius mark. The key is the type of star, as we discussed, and how its unique output interacts with the planet. The primary extra kick comes from the extreme ultraviolet radiation. This is not the gentle UV you get from a sunny day. This is hard, high-energy UV that carries photons with enough punch to break apart molecules in the planet's atmosphere. This process is called photodissociation, and it is not just about destroying water or methane. It is about converting the radiative energy directly into thermal energy. When a UV photon smashes into a molecule, it tears it apart into individual atoms, and that violent action releases heat, adding a significant boost to the atmospheric temperature. But the star does not stop there. It also bombards the planet with X-rays. These are even more energetic than UV photons, and they have the ability to penetrate and heat the very outer layers of the atmosphere to tens of thousands of degrees. This creates a monstrously inflated thermosphere, a region of the atmosphere that becomes so hot it puffs up and expands out into space, which is a major contributor to the atmospheric escape we observe. So, now we have direct radiative heating, plus heating from photodissociation, plus heating from X-ray absorption. But wait, there is more. The intense gravity and the tidal locking we mentioned play a crucial role in internal heating. Because the planet is so close and tidally locked, the gravitational pull from the star is not uniform. It flexes the planet's interior, much like squeezing a rubber ball repeatedly. This constant flexing, due to tidal forces, generates internal heat through friction. The core of the planet is being stretched and compressed, and that mechanical energy is converted into thermal energy, warming the planet from the inside out. This is similar to what happens on Jupiter's moon, Io, where tidal forces from Jupiter create intense volcanic activity, but on a much larger scale for this gas giant. This internal heating might help explain why the planet is so inflated. The extra heat from within could be contributing to the atmospheric expansion. Then, we have the potential role of magnetic interactions. The host star likely has a powerful magnetic field, and if the planet has its own magnetic field, the two can interact in dramatic ways. This interaction can create a circuit where magnetic energy is converted directly into heat, similar to processes observed in the auroras on Jupiter's moons. Charged particles could be funneled along magnetic field lines onto the planet's poles, generating immense, planet-wide auroras that dump enormous amounts of energy into the upper atmosphere. This could create localized hotspots and add another layer of heating that is not purely radiative. So, we have a cocktail of heating mechanisms: direct radiation from the star, photodissociation from UV, heating from X-rays, internal tidal heating, and potential magnetic heating. This combination is what elevates the temperature to levels that rival stars. It is not a single process, but a symphony of violent interactions that work together to create the inferno. The direct radiative heating sets the baseline, but the other factors amplify it significantly. For instance, the photodissociation process means that the atmosphere is not just absorbing heat, it is actively being torn apart, which releases additional energy. The X-ray heating ensures that the upper atmosphere is so hot that it is essentially boiling off into space, which also affects the energy balance. The internal tidal heating means that even without the star, the planet would have a significant heat source from within, though it would be much cooler. The magnetic heating, while still theoretical, could be the final piece that explains why the temperatures are so uniformly extreme. This multi-mechanism heating also affects the planet's weather and climate. The huge temperature difference between the day and night sides drives those supersonic winds. But the various heating sources ensure that the heat distribution is not simple. The day side is being cooked by all these processes simultaneously, while the night side, though shielded from direct radiation, still receives heat transported by winds and potentially from internal sources. This complex heating profile makes the planet a fascinating laboratory for studying atmospheric physics under extreme conditions. Understanding these mechanisms is crucial not just for this planet, but for all ultra-hot Jupiters. It helps astronomers refine their models of how planets interact with their host stars and how energy is transferred in such tight binary systems. Each mechanism contributes a certain percentage to the total heat budget, and figuring out that balance is an active area of research. Observations from telescopes like the James Webb Space Telescope are key here, as they can detect the signatures of these processes in the planet's spectrum. For example, by analysing the light that passes through the atmosphere during transit, scientists can identify the presence of atomic and ionic species that are created by photodissociation, and they can measure the temperature of the upper atmosphere to infer X-ray heating. Similarly, studying the planet's emission spectrum can reveal clues about internal heat distribution. The continuous evaporation of the atmosphere, driven by this intense heating, also plays a role in the energy balance. As the atmosphere escapes, it carries away heat, which might have a cooling effect. But the overall system is so dominated by the input of energy that the net result is still extreme heat. This evaporation process itself might generate additional heat through friction and hydrodynamic effects as the gas streams away from the planet. So, everything is interconnected. The heating mechanisms feed into each other, creating a self-reinforcing cycle of violence. The proximity to the star initiates the process, but the star's characteristics and the planet's own properties amplify it to unprecedented levels. This is why simply saying it is close to its star does not do justice to the reality. It is the specific combination of factors that makes this world so exceptionally hot. As we discover more planets like this, we will see variations in these mechanisms, which will help us understand the diversity of planetary systems. For instance, around a cooler star, even a close-in planet might not experience such intense UV and X-ray heating, so its temperature would be lower. Similarly, the strength of tidal heating depends on the orbital parameters and the planet's internal structure. By comparing different ultra-hot Jupiters, we can disentangle the contributions of each heating process. This knowledge is not just academic. It has implications for the search for habitable worlds. Understanding the extreme limits of planetary heating helps us define the boundaries of the habitable zone more accurately. If a planet is too close to an active star, these additional heating mechanisms could render it uninhabitable even if it were in the traditional zone. So, the study of this planet's heating is a lesson in the complexity of astrophysical systems and a reminder that simple models often fail to capture the full picture. The relentless, multi-source heating is what truly defines this world, making it a benchmark for extreme environments in our galaxy. With all that relentless multi-source heating pounding away at the planet, a natural question arises. Why hasn't this world simply vaporized into nothingness? The fascinating and somewhat counterintuitive answer is that it is actively evaporating, right before our eyes. But the process is happening at a rate that allows the planet to persist over human timescales, even as it bleeds mass into the void. This isn't a stable, serene world. It's a dynamic and leaky vessel in a cosmic storm. The primary driver of this atmospheric escape is the intense stellar radiation, particularly the high-energy ultraviolet and X-ray photons. which transfers enough energy to the gas molecules in the upper atmosphere to allow them to achieve escape velocity. Essentially, the star's radiation is continuously blowing the planet's atmosphere into space, and this isn't a gentle breeze but a violent, ongoing stripping. This process creates a vast, comet-like tail trailing behind the planet as it orbits, a stream of ionized gases being pushed away by the stellar wind and radiation pressure. Powerful spectrographs attached to major telescopes have detected the clear signatures of heavy elements within this evaporating stream, things like iron and titanium. But here is the real kicker. These elements aren't just present in a stable, solid state. They are detected as free atoms and even as ions, which is a physical impossibility on a normal, cooler planet where such metals would be locked into minerals or condensed into liquids. The energy environment is so intense that it can tear atoms apart, creating a plasma of charged particles that gets carried away in the stellar wind. This detection was a major clue that we were dealing with an atmosphere unlike any other. Now, within the atmosphere itself, even more bizarre weather is occurring. On the slightly cooler night side, where temperatures might drop to a mere 1,500 degrees Celsius, some of these gaseous metals can actually condense. Imagine clouds not of water vapour, but of liquid iron or titanium droplets, forming in the perpetual darkness. These aren't fluffy, white clouds. They are likely dense, metallic vapours that condense into mist-like particles of liquid metal. Then, driven by gravity, this metallic mist falls as rain, a shower of incandescent liquid iron droplets. But this is a tragic and short-lived existence for these metallic droplets. As they fall towards the lower, hotter layers of the atmosphere, or get swept by those supersonic winds back towards the dayside, they are quickly reheated and vaporized once again, returning to their atomic or ionic form. This creates a continuous violent cycle of evaporation and condensation, a meteorological phenomenon unique to these ultra-hot environments. It is a cycle of creation and destruction happening on a global scale, where elements are constantly changing state from gas to liquid and back again. So, if the planet is losing its atmosphere, why does it still exist? The rate of mass loss, while astronomically high in absolute terms, is still relatively small when compared to the planet's total mass. We are dealing with a gas giant that is several times the mass of Jupiter, an absolutely colossal amount of material. The current evaporation rate might be millions of kilograms per second, which sounds immense, but it is a tiny fraction of the planet's overall bulk. It is like a giant ice cube melting in the sun. It will take an incredibly long time to disappear completely. Estimates suggest that even at this high rate, it would take hundreds of millions, perhaps even billions, of years for the planet to lose a significant portion of its mass. Furthermore, the planet might have a deep, massive core that could remain even if the entire gaseous envelope was stripped away. Though that is a speculative idea, the evaporation process itself might also be self-limiting in some ways. As the outer atmosphere puffs up and expands due to the heat, it presents a larger cross-section for the stellar radiation to act upon, which could accelerate mass loss. However, the underlying gravity of the massive planet works to hold on to its atmosphere, creating a constant tug-of-war between radiation pressure and gravitational binding energy. The balance between these forces determines the evaporation rate. Scientists study this rate by observing the specific signatures of hydrogen and other elements in the planet's tail during transit. When the planet passes in front of its star, astronomers can sometimes detect a slight absorption signature from the extended atmosphere before and after the main transit, a clear indicator of this vast, escaping cloud of gas. This gives them a direct way to measure the scale and density of the evaporation. The presence of heavy elements like iron in the outflow is particularly telling. It indicates that the heating and stripping processes are so vigorous that they are reaching deep into the atmosphere, pulling up material that would normally be sequestered in lower, denser layers. This is not just a surface phenomenon, it is a deep atmospheric purge. The fact that we can detect these elements also helps astronomers calibrate their models of atmospheric escape, which has implications for understanding the evolution of other types of planets, including smaller, rocky worlds in close orbits around active stars. For those planets, such intense evaporation could strip away any potential atmosphere entirely, leaving behind a barren rock. So, this planet serves as a crucial laboratory for studying the limits of atmospheric retention. The continuous loss of mass also means the planet is slowly changing over time. Its gravitational pull is very gradually decreasing, which could have subtle effects on its orbit, though these are minuscule on short timescales. The composition of the remaining atmosphere might also be evolving, as lighter elements escape more easily than heavier ones, potentially leading to a gradual enrichment of heavier elements in the layers that remain. This whole situation paints a picture of a world in a state of flux, a temporary and dramatic phase in its life cycle. It is not a static inferno, but a dynamic one, actively being reshaped and diminished by its hostile environment. The evaporation is a direct consequence of the extreme heating mechanisms we discussed earlier, and it completes the picture of a planet living on the edge. It is being simultaneously cooked and blown away. Yet it is so massive that it can withstand this assault for eons. This resilience is a testament to the sheer scale of planetary bodies. The study of this evaporation process is a prime example of how observing extreme objects can teach us about universal physical processes. The principles of hydrodynamics, radiation transfer, and plasma physics that are at play here are the same ones that govern other astrophysical phenomena, from the winds of stars to the accretion disks around black holes. By understanding how a planet's atmosphere behaves under such duress, we improve our models for a wide range of cosmic events. Furthermore, the detection techniques pioneered for this world, such as high-resolution transmission spectroscopy of its extended envelope, are now being applied to other exoplanets, searching for similar signs of atmospheric escape. This expands our ability to characterize the diversity of planetary environments beyond our solar system. In the grand scheme, the planet's ongoing evaporation is a slow-motion death sentence, but one that provides a wealth of scientific insight. It is a stark reminder that planets are not permanent fixtures. They are dynamic systems that interact with their host stars in complex ways, and sometimes that interaction leads to a gradual, spectacular dissolution. The fact that we can observe this process in action is a remarkable feat of modern astronomy, allowing us to watch cosmic evolution unfold in real time, or at least on a timescale that we can model and understand. So, while the planet is indeed melting and bleeding into space, it is doing so in a way that reveals the profound and violent interconnectedness of stellar and planetary physics. The perpetual day side of this world is a thermodynamic nightmare beyond human comprehension, a place where the very concept of a solid surface becomes meaningless and the laws of chemistry as we know them are utterly suspended, bathed in the unrelenting, direct glare of its host star. This hemisphere experiences temperatures that surpass those of many red dwarf stars, making it one of the hottest known places in the entire universe. The radiation pouring onto this side is so ferociously intense that any and all molecules are immediately ripped apart. There is no water vapor, no carbon dioxide, no methane. Complex atomic bonds cannot hope to survive here. what remains is a sparse, searing soup of individual atoms and ions, a plasma where elements like iron, titanium, and silicon exist in their barest, most fundamental forms. The idea of a surface is nebulous at best because this is a gas giant, so there is no distinct ground to stand on. Instead, the atmosphere extends outward for thousands of kilometers, becoming progressively hotter and denser as you travel deeper into the planet's immense gravitational well. Though the traditional relationship between depth and pressure is complicated by the extreme external heating, the most fascinating detail about this blistering realm is that the point of maximum heat, the so-called hot spot, is likely not sitting directly at the substellar point, the spot that faces the star most directly. Sophisticated computer models and indirect observations suggest that the colossal supersonic winds racing from the day side to the night side actually push this hottest spot slightly downstream, eastward or westward from the centre. This indicates a dynamic atmosphere that is desperately trying to redistribute the insane amount of energy it absorbs, but failing to achieve any real balance. The colour of this hemisphere would be a blinding, incandescent white-blue glare, not merely reflecting starlight but glowing from its own intense heat, emitting a continuous spectrum of light much like a star itself. It is an environment where traditional weather, with clouds and rain, is replaced by the physics of plasma and hydrodynamic escape, where the dominant forces are radiation pressure and ionization. The atmospheric layers here are not stable. They are in a constant state of violent churn, with material being heated to the point of expansion and rising, while cooler, denser gas from deeper layers surges upward to replace it, only to be heated and expanded in turn. This creates a monstrous convection cycle that operates on a global scale. The term cooler is used relatively here, as these rising currents from the interior are still far hotter than any lava flow on Earth. The immense pressure deep within the atmosphere might create conditions where certain materials could exist in exotic states, like liquid metallic hydrogen, but the overwhelming heat from above ensures that the upper layers remain a dissociated atomic haze. The energy input is so tremendous that the atmosphere is effectively boiling away into space, as we discussed, with the day side being the primary source of this evaporative loss. The light emitted from the day side is so significant that astronomers can detect it directly when the planet passes behind its star, an event known as a secondary eclipse, by measuring the dip in infrared light as the planet disappears. Scientists can calculate the temperature of this scorching hemisphere. Furthermore, by observing how this infrared emission changes as the planet orbits, they can begin to map the rough temperature distribution, confirming the offset of the hottest spot and learning about the efficiency of heat distribution across the globe. The conditions are so extreme that they challenge the very definitions we use for planetary atmospheres. This is not an atmosphere in the terrestrial sense. It is more accurately a vast, extended, and low-density outer layer of a star-like object, a gravitationally bound exosphere that is being continuously ablated by its primary. The atomic species present are those with high dissociation energies, things like iron, magnesium, sodium, and silicon, all detected through their spectral signatures as they absorb specific wavelengths of starlight during transit. The absence of molecular bands in the dayside spectrum is a clear testament to the destructive power of the radiation. Any molecule that momentarily forms in a slightly denser pocket is immediately blasted apart by a photon. The soundscape, if one could survive to hear it, would be a perpetual, deafening roar, not of wind, but of atomic collisions and the sheer energy of photons striking atoms. The air itself, if it can be called air, would be thinner than in Earth's best laboratory vacuum at high altitudes, yet incandescently hot and glowing. the gravitational pull remains strong, a constant reminder that this is still a massive planet. But that gravity is fighting a losing battle against the radiation pressure that seeks to push the atmosphere away. The dynamics of this region are a key area of study for understanding the ultimate limits of planetary stability. How much radiation can a world withstand before its atmosphere is completely stripped? How do atmospheric circulation patterns function when the energy gradient is so immense? The Dayside provides a natural laboratory to test these questions. Its properties are not just academic curiosities. They inform models of planetary evolution for a whole class of objects, including rocky exoplanets orbiting close to their stars. The study of this hellish landscape tells us about the early history of our own solar system, when the young sun was more active and terrestrial planets like Mercury and Venus may have faced a less intense but similarly destructive environment. As we observe this planet with more advanced telescopes, each new data point refines our picture of this ultimate inferno. The James Webb Space Telescope, with its unparalleled infrared sensitivity, is particularly well suited to studying the thermal emission from the Dayside, potentially revealing variations in temperature and composition with a precision never before possible. This could allow us to create a crude weather map of this blazing world, showing the hot spots and the slightly less hot spots, and tracing the flow of energy as it is whipped around by those supersonic jets. In every conceivable way, the Dayside of this planet represents an extreme frontier, a place where normal physical rules are stretched to their breaking point and where our understanding of what a planet can be is constantly being rewritten. It stands as a stark counterpoint to the relative calm and familiarity of our own solar system, a reminder that the universe is capable of creating environments of breathtaking violence and majesty that defy easy imagination. In stark contrast to the incandescent hell of the permanent Dayside, the planet's opposite hemisphere exists in a state of perpetual night, a realm shrouded in eternal darkness that offers only a relative and deceptive refuge from the stellar fury. This is not a cool, peaceful place by any stretch of the imagination. It is merely less intensely heated, a distinction that still places it firmly in the category of an inferno, while the Dayside blazes at temperatures surpassing 4,000 degrees Celsius. The Nightside, shielded from the direct, unrelenting barrage of stellar radiation, experiences a dramatic plunge in heat. The temperatures here can drop to a range of 1,500 to 2,000 degrees Celsius. To put that into perspective, that is still hundreds of degrees hotter than molten lava erupting from a volcano on Earth. So the term cold is used here in the most relative sense possible. This significant temperature difference, thousands of degrees between the two hemispheres, is the primary engine driving the planet's bizarre and violent weather. Without the direct energy input from the star, the Nightside cools primarily through the emission of its own thermal radiation into the blackness of space, but it is far from a passive environment. The colossal thermal gradient between the day and night sides creates an immense pressure difference that powers supersonic winds. These are not gentle breezes but global, hurricane-force jets of gas screaming across the terminator, the line that separates day from night, at speeds of thousands of kilometers per hour. These winds act as a planetary-scale heat pump, desperately attempting to equalize the impossible temperature imbalance by transporting scorching hot gas and vaporized material from the Dayside into the eternal night. This constant influx of heat from the winds prevents the Nightside from cooling down even further, maintaining it at those still astronomical temperatures. The relative coolness of the Nightside has a profound effect on the local chemistry, which is the most intriguing aspect of this hemisphere. On the Dayside, molecules are instantly obliterated by high-energy photons. But here, in the darkness, the lower energy environment allows for a brief respite. atoms that were torn apart on the day side, carried over by the winds, now have a chance to briefly recombine into simple molecules. You won't find complex organic molecules or anything resembling life, but you might get transient formations of simple compounds like titanium oxide or silicon monoxide. This is a fleeting chemistry, happening in a world where bonds are constantly made and broken. Furthermore, the drop in temperature allows for a phenomenon that sounds like it's straight out of science fiction: the condensation of metals. Elements like iron and titanium, which exist as a vaporized gas on the day side, can actually cool enough on the night side to condense into liquid droplets. This leads to the formation of exotic, metallic clouds. Imagine clouds not of water, but of liquid iron, hanging in a sky of perpetual black. And just like on Earth, where water vapor condenses and falls as rain, these metallic clouds can precipitate. So, on this planet's night side, it could literally rain droplets of liquid iron and titanium. This metallic rain would be a surreal spectacle, a shower of incandescent, liquid metal falling through the dense, hot atmosphere. However, this is a tragic and short-lived existence for these newly formed molecules and metallic droplets. The same supersonic winds that brought the material to the night side are part of a global circulation pattern that eventually drags everything back towards the day side. Any molecule that manages to form, any droplet of iron that condenses, is doomed. As it is circulated back across the terminator into the blinding light and intense heat of the day side, it is instantly flash vaporized and dissociated back into its atomic components. This creates a continuous dot, violent cycle of destruction and partial rebirth. A meteorological loop of unimaginable ferocity. The entire atmosphere is thus in a state of constant, turbulent churn, with material endlessly cycling between the two hemispheres. This cycle is not efficient or smooth. It is chaotic and driven by extreme forces, likely generating massive storm systems and vortices on a scale we can barely model. The dynamics are so intense that they might involve phenomena like shock waves and sonic booms within the atmosphere itself as gas moves at supersonic speeds. The night side, therefore, is not a stable, separate entity but an integral part of a single, globally connected weather system. Its conditions are entirely dictated by what happens on the day side. Studying this hemisphere is crucial for understanding the planet's energy budget and atmospheric circulation. By measuring the temperature of the night side through its infrared emissions, astronomers can calculate how efficiently heat is being transported from the day side. A colder night side would suggest less efficient heat distribution, while a warmer one indicates those supersonic winds are doing a formidable job. Observations from telescopes like the James Webb Space Telescope are vital for this, as they can detect the subtle differences in the infrared glow between the two hemispheres, the presence of certain molecular signatures in the night side spectrum, however faint and temporary, provides direct evidence of this recombination chemistry and allows scientists to probe the conditions there. The night side also holds clues about the planet's internal structure and potential magnetic field. If the planet has a magnetic field, its interaction with the stellar wind might be different on the night side, potentially creating a more protected region or generating auroral phenomena. However, the environment is so hostile that even these interactions would be incredibly energetic. The perpetual darkness also means that there is no light source other than the faint glow from the heated atmosphere itself and the occasional flash of lightning from within the metallic clouds, if such electrical activity occurs. This world's stark duality serves as a powerful reminder of how tidal locking can create two dramatically different environments on the same planetary body. It is a natural laboratory for studying atmospheric dynamics under the most extreme forcing imaginable. The processes at work here, while magnified to an unbelievable degree, have parallels in our own solar system, such as the temperature differences on Mercury or the atmospheric circulation on Venus, but they are taken to a terrifying extreme. Understanding this night side helps astrophysicists test the limits of their climate and fluid dynamics models, pushing computational capabilities to their brink. It also has implications for the study of other tidally locked worlds, including potentially habitable planets around red dwarf stars, where understanding the day-night heat transport is key to assessing their climate stability. So, while the night side might be called a refuge, it is a desperate and violent one, a key player in the planet's ongoing drama of evaporation and heat. It is a place of temporary condensation amidst a perpetual storm, a slightly less brutal corner of a world that defies categorization and continues to challenge our understanding of what is possible in the universe. The perpetual churn between the day and night sides sets the stage for a chemical landscape that is as bizarre as it is informative. A place where the very elements that make up the world are laid bare in their most fundamental forms. This planet's atmosphere acts as a colossal, natural laboratory for studying chemistry under conditions of extreme temperature and pressure that we could never hope to replicate on Earth. The first and most striking feature of its composition is the complete and total absence of the molecules we typically associate with planetary atmospheres. You will find no water vapour here, no methane, no ammonia, no carbon dioxide. The reason is simple and brutal. The intense ultraviolet radiation from the star instantly photodissociates any such complex molecules, tearing them apart into their constituent atoms before they can even form or persist. In their place, we find a raw dot, elemental soup, a plasma where the periodic table is displayed in a wild and unbound state, high-resolution spectroscopy, which analyses the starlight filtering through the planet's atmospheric rim during transit, has revealed a stunning array of elements that are usually hidden deep within the interiors of rocky planets. We are talking about things like titanium, vanadium, dot, iron, and even traces of rare earth elements, all floating freely in the gaseous state. This is not an environment where these metals are locked into minerals or rocks. They are vaporized and available for detection, giving us a direct sample of what might be the planet's deep interior composition. The detection of these elements is a technical marvel, requiring incredibly precise instruments and sophisticated data analysis to pick out their faint spectral signatures from the overwhelming glare of the host star. What is even more fascinating is the specific forms these elements take. Because the temperatures are so high, we can detect not just neutral atoms, but also their ionized counterparts. For instance, astronomers have found clear signatures of both neutral iron and singly ionized iron, meaning iron atoms that have lost one electron. This is a clear indicator of the intense radiative environment, as it takes a significant amount of energy to strip electrons from atoms. Furthermore, in the slightly cooler niches, particularly on the night side or in deeper atmospheric layers, some simple, robust molecules can briefly form. Species like titanium oxide, silicon monoxide, DOT, and aluminum hydride have been tentatively identified. These are known as high-temperature molecules because they can only exist and be stable at the scorching temperatures that would instantly destroy any organic compound. Their detection is a crucial benchmark for validating our theoretical models of atmospheric physics and chemistry. If our models can correctly predict the presence and abundance of these exotic species in such a hellish environment, it gives us greater confidence in applying those same models to more temperate, potentially habitable worlds. The study of this chemistry is not merely about cataloguing oddities. It has profound implications for the entire field of exoplanet science. by understanding the spectral fingerprints of these hot, metal-rich atmospheres, we learn to distinguish them from the potential biosignatures we might one day find on Earth-like planets. For example, the signature of titanium oxide or vanadium oxide could potentially mimic or obscure the signal of gases like oxygen or methane in lower resolution data. Therefore, characterizing this world in extreme detail helps us refine our search strategies for life elsewhere. It teaches us what to look for and, just as importantly, what to ignore as a false positive. The processes at work here also inform our understanding of planetary formation and evolution. The presence of such heavy elements in the atmosphere suggests that the planet either formed from material rich in these metals or that its intense heat is dredging up material from deep within its interior. For a gas giant. This could mean that we are indirectly sampling the composition of its core or lower atmospheric layers, which are normally inaccessible to observation. The continuous evaporation and the global circulation patterns ensure that this chemical soup is constantly being stirred and mixed, providing a fairly homogeneous sample on a global scale, albeit with variations between the day and night sides. The day side, as we know, is too hot for anything but atoms and ions, while the night side allows for that brief, tantalizing moment of molecular recombination before everything is destroyed again. This cycle is not just about destruction. It is a dynamic process that drives chemical reactions we can only dream of studying in a lab. The energy inputs are so enormous that they can push reactions into regimes that are not favorable under normal conditions. This makes the planet a testing ground for fundamental chemical principles under extreme duress. Every new observation, especially from powerful telescopes like the James Webb Space Telescope, adds another piece to this complex puzzle. JWST's infrared capabilities are ideal for detecting the thermal emission and absorption features of these metal oxides and hydrides, potentially allowing us to map their distribution across the planet's atmosphere. We might even be able to determine if certain elements are more abundant on the day side or the night side, which would tell us about the efficiency of atmospheric transport and condensation cycles. For instance, if iron is condensing and raining out on the night side, we might detect a slight depletion in its gaseous form there compared to the day side. This level of detail is what transforms a curious discovery into a deep scientific insight. The exotic chemistry also has implications for understanding the star itself. The types of elements present and their abundances can reflect the composition of the protoplanetary disk from which the system formed, offering clues about the stellar nucleosynthesis and the initial conditions of planet building. It is a window into the raw materials available in that particular region of the galaxy. Furthermore, studying how these elements behave under such intense radiation helps astrophysicists refine models of stellar atmospheres and the interactions between stars and their planets. The line between stellar and planetary physics becomes blurry here, and that is exactly what makes it so compelling. In the grander search for life, this world serves as a crucial baseline. It defines the extreme, uninhabitable end of the planetary spectrum. By comprehending the absolute limits of chemical complexity under such violence, we can better appreciate the delicate and rare conditions that allow for the chemistry of life to flourish on worlds like our own. It humbles us and excites us simultaneously, showing both the destructive power and the creative diversity of the cosmos. So, while this planet's atmosphere may be a terrifying and alien place, its value to science is immense. It is a reference point, a natural experiment, and a reminder that the universe is capable of wonders that constantly challenge our imagination and expand our understanding of what is possible. So, after unraveling the exotic chemistry of this blazing world, we are left with a fundamental puzzle that strikes at the very heart of how planetary systems are born. How did a gas giant of such immense proportions end up in an orbit so tight it defies conventional wisdom? This is the Great Formation Enigma, a question that forced astronomers to rethink their models from the ground up. The standard theory of planet formation, built largely from our understanding of our own solar system, paints a clear picture for gas giants like Jupiter. They are thought to form in the cold, outer regions of a protoplanetary disk, the vast swirl of gas and dust surrounding a young star. In these distant, frigid zones, beyond what is called the frost line, temperatures are low enough for volatile compounds like water, ammonia, and methane to freeze into solid ice grains. These icy particles act as sticking agents, allowing dust and rock to clump together more efficiently, building up planetary cores through collisions and accretion. Once a solid core reaches a critical mass, typically around 10 times the mass of Earth, its gravity becomes strong enough to rapidly pull in and hold onto vast amounts of hydrogen and helium gas from the surrounding disk, snowballing into a gas giant. This entire process requires a cold, stable environment and plenty of time, on the order of millions of years. Now, place that same process right next to a young, hot, and massive star. The environment is utterly hostile. The region is searingly hot, far above the condensation points for ices, meaning those crucial sticky materials cannot exist in solid form. The disk material itself would be too warm and turbulent, preventing the slow, gentle accretion of dust grains into larger bodies. The intense radiation and stellar winds from the young star would blow away any loose gas, making it nearly impossible for a planet to gather a massive atmosphere. Furthermore, the orbital dynamics are chaotic. The gravitational pull is so strong that any forming clumps would be torn apart or spiral inward quickly. So, the in situ formation of a planet like this, right where we find it, is practically impossible. This left scientists with one compelling alternative: migration. The leading hypothesis is that this planet did not form in its current scorching orbit but was born much farther out, in a cooler, more placid region of the disk similar to where Jupiter resides in our system. After its core formed and it accumulated its gaseous envelope, something caused it to move, to journey inward from its birthplace toward the star. This planetary migration is a key process in modern astrophysics, and it can happen in a couple of primary ways. The first is disk migration. A young planet embedded in the protoplanetary disk interacts gravitationally with the gas and dust. These interactions can create torques that either push the planet inward or pull it outward. For a massive planet, the most common outcome is Type II migration, where the planet's gravity carves a gap in the disk. The planet then gets locked into this gap and follows the inward flow of the disk material as it accretes onto the star. This process can drag a planet from orbits taking years to complete down to orbits taking mere days. The second mechanism involves gravitational interactions with other planets in a crowded young system. The gravitational pull between multiple giant planets can fling one inward on a highly elliptical orbit while throwing another outward. Over time, gravitational tugs with leftover planetesimals or tidal interactions with the star can circularize that eccentric orbit into a tight, close-in path. So, the planet likely embarked on a grand inward journey. But this migration story has a critical catch. It had to stop. If the migration process continued unchecked, the planet would have spiraled directly into the star and been consumed. The fact that we see it today means something acted as a braking mechanism, halting the migration precisely at its current orbital distance. Figuring out what that brake was is a major focus of research. One possibility is that the migration ceased when the protoplanetary disk dissipated, as the young star aged. It blew away or accreted the remaining gas and dust in the disk, removing the material that was driving the migration and effectively stranding the planet in its close orbit. Another idea involves the star's own magnetic field and the inner edge of the disk. The disk might be truncated at a certain distance from the star due to magnetic interactions, creating a natural parking spot for migrating planets. Tidal forces between the planet and the star could also play a role, eventually balancing the migratory forces and stabilizing the orbit. The precise halting mechanism might be unique to each system, depending on the star's mass, the disk's properties, and the planet's own characteristics. Studying this particular world provides crucial data to test these migration models. Its existence confirms that large-scale planetary migration is not just a theoretical idea, but a common and dramatic process in the universe. It tells us that planetary systems are dynamic and often violent places, where planets are not necessarily born in the orbits where they reside for most of their lives. This has profound implications for our understanding of our own solar system. While we don't have any hot Jupiters here, the migration of Jupiter and Saturn early in the solar system's history is thought to have influenced the formation of the inner terrestrial planets and the structure of the asteroid belt. The discovery of this extreme world and others like it has expanded the known diversity of planetary architectures, showing us that configurations we once thought were rare or impossible are actually quite common. This enigma also ties into the planet's ultimate fate. Its current orbit might not be perfectly stable over billions of years. Tidal forces could still be causing a very slow orbital decay, leading it on a long-term spiral into the star. Alternatively, as the star evolves into a red giant, it will expand and likely engulf the planet anyway. So, the migration that brought it here is also part of the narrative that will lead to its destruction. Understanding formation through migration helps astronomers predict what kinds of planets might be found around different types of stars and informs the search for habitable worlds. If giant planets routinely migrate inward, they could disrupt or eject smaller, Earth-like planets from the habitable zone, affecting the potential for life in those systems. By refining migration models with data from this planet, we get better at assessing the likelihood of stable, life-friendly environments elsewhere in the galaxy. So, the enigma of its formation is more than just a curiosity about one weird world. It is a window into the fundamental processes that shape all planetary systems. It challenges our assumptions, drives theoretical innovation, and reminds us that the cosmos is far more mobile and eventful than a static model would suggest. The journey from a cold, distant birth to a blazing, close in existence is an epic tale written in gravity and gas, and we are just beginning to read the chapters. The mystery of how this planet arrived in its blistering orbit leads us directly to the ongoing, dynamic relationship it shares with its host star, an interaction that is far more intimate and violent than a simple transfer of light and heat. This isn't a one-way street where the star does all the work and the planet passively show it. This is a full-fledged, titanic battle of forces where both bodies exert a measurable influence on each other, given its substantial mass and incredibly close proximity. The planet is not just a speck orbiting a giant. It is a significant gravitational player in the system. This gravitational tug, however subtle, can actually cause noticeable effects on the star itself. For instance, the planet's pull can influence the star's rotation, potentially slowing it down or causing subtle distortions over time. It might even contribute to the formation or behaviour of star spots, those cooler or darker regions on the stellar surface. By affecting the convective flows and magnetic dynamics within the star's outer layers, this means the planet is literally leaving a fingerprint on its sun. a gravitational signature that astronomers can potentially detect through careful long-term monitoring. But the gravitational interaction is only part of the story. The real drama unfolds in the realm of magnetism and plasma. The host star, being a hot, massive type A or B star, likely possesses a powerful and complex magnetic field. Now, if the planet has its own magnetic field, which is a subject of intense speculation and modelling, then the two fields can become directly linked. Imagine a giant, invisible magnetic bridge connecting the star to the planet. This connection can create a colossal electrical circuit, where charged particles flow along the magnetic field lines from the star to the planet's poles. When these high-energy particles slam into the planet's upper atmosphere, they deposit immense amounts of energy, creating localized heating that could far exceed the already insane background temperatures. This process is similar to what causes auroras on Earth, but on a scale that is almost incomprehensible. We are talking about auroras that would be billions of times more energetic than our northern lights, potentially enveloping the entire planet in a permanent, ghostly glow of X-rays and ultraviolet light. This isn't just a pretty light show. It's a fundamental heating mechanism that adds another layer of complexity to the planet's energy budget. Then there is the relentless assault of the stellar wind. This isn't a gentle breeze. It's a supersonic torrent of charged particles constantly flowing from the star. Because the planet orbits so close, it is fully immersed in this violent stream. The stellar wind slams directly into the planet's magnetosphere, which is the region of space dominated by its magnetic field. This collision compresses the magnetosphere on the day side, crushing it inward, and stretches it out on the night side into a long, comet-like magnetotail. If the stellar wind is strong enough and the planet's magnetic field is weak, this interaction can effectively erode the magnetosphere, stripping it away and leaving the atmosphere even more exposed to direct bombardment. This erosion could accelerate the atmospheric evaporation we observe, as the protective magnetic bubble is compromised. The interaction is a two-way street. Just as the star affects the planet's presence can disturb the star's own magnetic field and the flow of its wind. The planet acts like a rock in a stream, creating a wake and potentially triggering instabilities in the stellar corona. In some extreme cases, for very close-in planets, this interaction might even generate observable radio emissions, as the magnetic reconnection events release bursts of energy. Detecting such radio signals is incredibly challenging, but would provide direct evidence of this magnetic dance. The entire system is thus a coupled oscillator, where energy and momentum are constantly being exchanged. This star-planet interaction is not a static picture. It's a dynamic process that evolves over time. As the star goes through its own activity cycles, with periods of high and low magnetic activity, the intensity of the interaction will wax and wane. During a stellar flare or a coronal mass ejection, the planet would be subjected to a sudden, catastrophic increase in radiation and particle flux, potentially stripping away large chunks of atmosphere in a single event. This means the planet's environment is not consistently hellish. It experiences violent storms and tempests of stellar activity that make its conditions even more extreme temporarily. Studying this interaction requires a multi-wavelength approach. Astronomers use data from X-ray observatories to look for signs of heightened activity correlated with the planet's orbit. They use ultraviolet telescopes to study the atmospheric evaporation and any potential auroral emissions. And they use optical and radio telescopes to monitor the star for changes. Each observation adds a piece to the puzzle. Understanding this relationship is crucial for painting a complete picture of the planet's current state and its ultimate fate. The energy dumped into the planet through these magnetic and gravitational channels contributes to its overall inflation and helps drive the violent weather systems we see. It's a key part of the reason why this world is so extreme. Moreover, this isn't just about one planet. Studying this system provides a template for understanding other close-in planetary systems, especially those around active stars. It shows us that planets are not isolated islands, but are deeply integrated with their host stars in a complex, often destructive, tango. The forces at play here, gravity and electromagnetism, are the same fundamental forces that shape all cosmic structures, but they are operating in a regime of extreme proximity and intensity that pushes our models to their limits. This ongoing battle between star and planet is a powerful reminder of the interconnectedness of cosmic objects. It blurs the line between stellar and planetary physics, creating a new subfield of study focused on these intimate interactions. As we discover more ultra-hot Jupiters and other close-in worlds, we will see a spectrum of such relationships, each with its own unique characteristics. This particular world, with its record-breaking temperatures and extreme orbit, serves as a benchmark, a worst-case scenario that helps us understand the boundaries of what is possible. So, while the planet is undoubtedly a victim of its star's fury, it is also an active participant in a dramatic cosmic dance, a dance that shapes its atmosphere, drives its weather, and ultimately contributes to its slow destruction. This intricate interplay is what makes the system so fascinating to astronomers. It's a natural laboratory for plasma physics, magnetohydrodynamics, and orbital dynamics, all wrapped into one blazing, terrifying, and beautiful package. The intense and violent interactions between the star and the planet we just explored are not a permanent state of affairs. They are part of a slow, inexorable countdown to a definitive and catastrophic end. The future of this world is intrinsically tragic, a story written in the unforgiving laws of physics that guarantees its destruction on cosmic timescales, making its current blazing existence a fleeting and dramatic phase. The primary threat comes from its incredibly tight orbit. The same tidal forces that have locked the planet, forcing one face forever towards the star, are also likely causing its orbit to decay very gradually. This is a process known as orbital decay, where gravitational interactions between the two bodies slowly convert orbital energy into heat within the planet, causing it to spiral inward over millions of years. It is a slow but relentless drag, a gravitational dance that is slowly losing energy. Even if the tidal forces were not strong enough to cause a rapid decay, the planet faces another, even more certain doom from the evolution of its host star. Remember, this is a massive, hot star, and such stars live fast and die young. While our sun will shine steadily for billions of years, this star is burning through its nuclear fuel at a prodigious rate, in a relatively short time. Astronomically speaking, perhaps only a few tens of millions of years, it will exhaust the hydrogen in its core and begin to evolve off the main sequence. It will swell dramatically into a red giant, a phase where its outer layers expand to hundreds of times their current size. When this happens, the star's radius will easily surpass the planet's current orbital distance. The planet, orbiting so close, will find itself inside the star's extended atmosphere. It will be completely engulfed, vaporized by the intense heat and friction, its material assimilated into the star without a trace. This is a common fate for planets orbiting close to massive stars, but the speed of this process here is breathtaking. The entire life cycle of this system, from formation to destruction, is compressed into a cosmic blink compared to the multi-billion-year history of our own solar system. But even before this final act of stellar engulfment, the planet is undergoing a slower form of disintegration. The continuous evaporation of its atmosphere, driven by the intense stellar radiation, is a constant drain on its mass. While the rate is slow relative to the planet's total bulk, it represents a steady erosion, a gradual whittling away of its substance over hundreds of millions of years. This process alone would not destroy the planet completely in the short term, but it contributes to its gradual demise, especially when combined with the other forces. So, we have a multi-pronged attack on the planet's existence, a potential slow spiral inward due to tidal decay, the certain future of stellar engulfment, and the continuous bleeding of its atmosphere into space. This makes the planet a transient object, a temporary wonder in the galaxy. Studying it is like catching a glimpse of a spectacular but short-lived firework in the cosmic night. Its value to science lies in this very transience. It allows us to observe and model processes that are crucial for understanding the evolution of planetary systems. The rate of orbital decay, DOT, for instance, tells us about the strength of tidal interactions and the internal structure of both the star and the planet. By monitoring the planet's transit times with extreme precision over years, astronomers can look for tiny changes in its orbital period, a telltale sign of this decay. Similarly, the rate of atmospheric evaporation provides insights into how planets lose their envelopes and under what conditions a gas giant might be stripped down to its core, potentially creating a new class of Chthonian planets. The impending stellar evolution offers a preview of the fate that awaits many inner planets in systems with massive stars. It helps us understand the late stages of stellar life and how planets interact with their dying hosts. This knowledge is not just academic. It has implications for our understanding of the chemical enrichment of the galaxy, as the material from evaporated and engulfed planets is recycled into the interstellar medium, eventually forming new stars and planets. The study of this world, therefore, connects the life cycles of planets to the life cycles of stars. It shows that planetary systems are dynamic and ever-changing, not static sculptures in space. The discovery of such an extreme object forces us to confront the fact that many of the planets we see today might not exist in a billion years, and that the architectures of planetary systems are constantly in flux. This perspective is humbling and exhilarating. It means we are witnessing a snapshot in an ongoing cosmic drama. The planet's inevitable destruction also raises profound questions about the nature of habitability and the long-term stability of planetary environments. While this world is itself utterly uninhabitable, its fate underscores the fact that even planets in more temperate zones can be vulnerable to the evolution of their stars. Understanding the timescales and processes involved in stellar evolution and planetary orbital dynamics is crucial for assessing the long-term potential for life on any world. In a way, this hellish planet serves as a cautionary tale about the fragility of worlds in the face of stellar power. Yet, from a scientific standpoint, its value is immense. It is a natural laboratory for testing theories of tidal orbital decay, atmospheric escape, and stellar evolution under extreme conditions. Each observation we make, each new data point from telescopes like the James Webb, adds to our understanding of these fundamental processes. The planet's story is a reminder that destruction and creation are intertwined in the cosmos. Its eventual demise will contribute material to the galaxy, and the knowledge we gain from studying it will contribute to our understanding of the universe. So, while its future is one of certain destruction, its present is a gift to science, offering a rare and detailed look at the violent and dynamic processes that shape the lives of planets and stars. As we continue to observe it, we are not just watching a world die. We are learning about the life cycle of planetary systems, gaining insights that will help us interpret the fates of countless other worlds throughout the galaxy. This makes the study of this planet not a morbid fascination with an ending, but a crucial chapter in our ongoing quest to understand the story of the universe and our place within it. The planet's tragic destiny is, in its own way, a key to unlocking broader cosmic mysteries, considering the grim and inevitable fate awaiting this blazing world. One might wonder how we can possibly know so much about a planet that is actively being destroyed from billions of kilometers away. The answer lies in a suite of incredible observation techniques that act as our remote eyes and ears, allowing us to decipher the secrets of this cosmic inferno despite the overwhelming challenges. Peering into the glare of such a stellar furnace requires cutting-edge technology and some of the most sophisticated data analysis methods ever developed by astronomers. The primary workhorse for discovering and studying planets like this is the transit method. This involves continuously monitoring the brightness of the host star over long periods, watching for those telltale, periodic dips in light that occur when the planet passes directly in front of the star from our point of view. For a typical exoplanet, this dip is already incredibly subtle, but for this particular world, the challenges are multiplied. The planet, while a gas giant, is still physically small compared to the vast disk of its host star, and its incredibly rapid orbital period means these transits are extremely brief and frequent, sometimes lasting only a matter of hours. Detecting such a faint and fast signal demands telescopes with exceptionally high photometric precision, instruments capable of measuring changes in brightness with a stability that seems almost impossible, ground-based surveys using networks of automated, wide-field telescopes were often the first to flag these unusual signals, but confirming them and extracting detailed information requires a global effort and coordination with larger observatories. Once a transit is detected and the planet's existence is confirmed, the real detective work begins with spectroscopy. This is where we move from simply knowing the planet is there to understanding what it is actually made of. The most powerful technique for this is called transmission spectroscopy. During the precious minutes when the planet is transiting, a tiny fraction of the star's light filters through the planet's atmosphere. As this light passes through the atmospheric rim, certain wavelengths are absorbed by the atoms and molecules present there. By comparing the star's spectrum when the planet is in front of it to the spectrum when it is not, astronomers can identify these missing wavelengths, each one a unique fingerprint of a specific element or molecule. It is like taking a spectral biopsy of the planet's atmosphere from a mind-boggling distance. This is how we know about the presence of vaporized iron, titanium, and other exotic elements. Their absorption lines appear in the data, telling a story of an atmosphere stripped down to its atomic components. Another crucial technique is emission spectroscopy. This focuses on the light coming directly from the planet itself, primarily the intense infrared radiation emitted by its scorching day side. We can measure this light during a secondary eclipse, which is when the planet moves behind the star from our perspective. The total light from the system drops by a tiny amount, the contribution from the planet itself, and by measuring that dip, we can determine the planet's temperature. Even more impressively, by taking spectra during this phase, we can map the temperature gradient across the planet's atmosphere and even begin to understand the heat distribution between the permanent day and night sides. This helps us validate models of those supersonic winds and global heat transport. Doing all of this from the ground is incredibly difficult because Earth's atmosphere absorbs and distorts much of the infrared light we need to detect. That is why space observatories have been utterly transformative for this field. The Hubble Space Telescope, with its sensitive optics above the atmosphere, has provided invaluable data, particularly in the ultraviolet and optical ranges, helping to study the atmospheric evaporation and the presence of certain elements. The Spitzer Space Telescope, before its mission ended, was a pioneer in infrared exoplanet science, giving us our first real insights into the thermal properties of these hot worlds. But the game changer, the instrument that is truly revolutionizing our understanding, is the James Webb Space Telescope. JWST is an infrared powerhouse, designed with exoplanet atmospheres in mind. Its giant mirror and suite of incredibly sensitive instruments, like NIRSpec and MIRI, can obtain transmission and emission spectra with a clarity and detail we never thought possible. It can detect the signatures of molecules that only exist at high temperatures, map temperature variations across the planet's face, and probe deeper into the atmospheric structure than ever before. The data from JWST is not just confirming old theories. It is opening up new questions and revealing complexities we never anticipated. For instance, it might help us understand the precise chemistry on the night side, or detect the presence of unexpected compounds. The analysis of this data is a science in itself. The raw signals are incredibly faint, buried in noise from the star and the instruments themselves. Extracting a clean spectrum requires complex algorithms and statistical models, often run on powerful supercomputers. Astronomers have to carefully remove instrumental effects, correct for stellar activity like spots and flares, and model the intricate physics of the atmosphere to interpret what they are seeing. It is a painstaking process of iterative modeling and validation. Every tiny dip or wiggle in the light curve has to be scrutinized. Furthermore, observing such a system requires precise timing and coordination, as the transits and eclipses happen so quickly. Miss the window by a few minutes, and you have to wait for the next orbit, which, fortunately, is only hours away. This frequent cadence is a double-edged sword. It provides lots of data quickly, but it also demands immense telescope time and rapid data processing. The role of radial velocity measurements remains important too. While not a direct imaging technique, it provides the planet's mass by measuring the star's wobble. Combining the mass from radial velocity with the size from the transit method gives us the planet's density dot, which is how we know it is a puffed up, low-density world. This fundamental parameter is crucial for understanding its internal structure and why it has such an extended atmosphere. The future of observing these worlds is equally exciting. New missions and telescopes are on the horizon. The European Space Agency's Plato mission will be a transit surveyor on a massive scale, designed to find thousands more exoplanets, including hopefully more of these extreme examples to build up statistical knowledge. Meanwhile, giant ground-based telescopes like the Extremely Large Telescope, with a mirror 39 meters across, will attempt the Herculean task of direct imaging. They will use advanced coronagraphs to block out the overwhelming light of the star, trying to capture the faint pinpoint of light from the planet itself. This would be a monumental achievement, allowing us to potentially see the planet as a separate entity and study its properties in a completely different way. In essence, the study of this planet is a triumph of remote sensing. We are using the laws of physics as our tool, interpreting the subtle interactions of light and matter across the void. It is a testament to human curiosity and ingenuity that we can infer the existence of iron rain and supersonic winds on a world we will never visit. Each observation is a piece of a puzzle, and with every new telescope and every improved technique, the picture becomes clearer, revealing not just the nature of this one bizarre world, but expanding our understanding of the vast and diverse family of planets that fill our galaxy. The story of this planet is written in light, and we are only just learning how to read it. So, having explored the sophisticated tools that allow us to spy on this distant world, Let's dive headfirst into the chaotic and utterly bizarre weather patterns that define its existence, a realm where the very concept of meteorology is rewritten. The observations we've gathered paint a picture of an atmosphere in perpetual, violent turmoil, driven by the most extreme temperature gradient imaginable. On one side, you have the permanent day, a blistering landscape where temperatures soar beyond 4,000 degrees Celsius, hot enough to tear molecules apart into individual atoms. On the other, the eternal night, a domain that, while still hotter than any lava flow on Earth, is thousands of degrees cooler. This isn't just a difference, it's a thermodynamic cliff face, and the atmosphere is constantly falling off it, giving rise to weather phenomena that defy belief. The most dominant feature of this global climate system is the wind. These are not gentle zephyrs or even the powerful gusts of a terrestrial hurricane. These are supersonic jets of gas screaming across the planet at speeds that can reach many thousands of kilometers per hour. To put that in perspective, the speed of sound in this hot, thin atmosphere is itself incredibly high, but these winds exceed it, making them truly supersonic. They are born from the simple, brutal physics of pressure difference. The intensely heated gas on the day side expands, creating a region of high pressure, while the cooler, denser air on the night side creates a low pressure zone. The atmosphere, seeking equilibrium, rushes from high to low pressure, but the scale and intensity are so vast that this flow accelerates to unimaginable velocities. These winds act as a planetary scale heat engine, desperately attempting to ferry thermal energy from the day side to the night side. They flow in a relentless torrent, carrying with them the vaporized remains of what might have been a more typical planet. Atoms of iron, titanium, silicon, and other heavy elements that were blasted apart by the stellar radiation as this scorching hot gas crosses the terminator into the perpetual darkness of the night side. It begins to cool, now. Cool is a relative term here. We are still talking about temperatures that could melt tungsten, but it is enough of a drop to initiate a phase change. The kinetic energy of the atoms decreases just sufficiently for them to start clumping together. This is where the magic, or rather, the terrifying physics, happens. Elements like iron and titanium, which exist as a thin, atomic vapor on the day side, begin to condense into liquid droplets. They form clouds, but these are not the white, fluffy cumulus we know. They are dark, metallic clouds, a mist of liquid iron and titanium hanging in the black sky, and when these clouds become saturated, it rains. It rains droplets of molten metal. Picture a shower of incandescent, liquid iron falling from the sky. A surreal and beautiful yet horrifying spectacle. This metallic precipitation doesn't last long. The droplets, driven by gravity, begin to fall towards the deeper, hotter layers of the atmosphere simultaneously. The global wind circulation is constantly dragging material back towards the day side, as the droplets descend or are swept back into the light. They are rapidly reheated. Before they can travel far, they are flash vaporized, turning back into a gaseous state, ready to be carried by the winds once more to the night side to repeat the cycle. This creates a perpetual, violent loop of evaporation, condensation, and precipitation, a meteorological process unlike any other we know. The entire atmosphere is thus in a state of constant, churning recycling. The turbulence involved in this cycle is immense. The supersonic winds do not flow smoothly. They shear and interact, creating colossal vortices and storm systems that could engulf entire Earths. The interaction between the fast-moving gas and the condensing metals likely generates incredible electrical activity, with lightning strikes that could be thousands of times more powerful than anything on our planet, arcing through clouds of liquid iron. The sound, if one could hear it, would be a continuous, deafening roar of wind and thunder, a symphony of destruction. Studying this extreme weather is not just an academic exercise in cataloguing cosmic oddities, it is a crucial window into fundamental physics. The conditions on this planet represent a natural laboratory for fluid dynamics and thermodynamics operating in regimes we cannot hope to replicate on Earth. How do gases behave when flowing at supersonic speeds under such colossal temperature and pressure gradients? How do materials change phase when the energy involved is so tremendous? The data we get from this world allows us to stress test our computer models to their absolute limits. These models, which simulate atmospheric circulation, heat transfer, and chemistry, are essential for understanding not just this planet, but all planets. The principles refined here help us interpret the climate of other hot Jupiters, the weather on brown dwarfs, and even the atmospheric dynamics of younger, more active versions of our own gas giants. Furthermore, this research pushes the boundaries of planetary science itself. It demonstrates that meteorology can encompass elements and processes far beyond water and carbon-based chemistry, involving the entire periodic table in a dynamic dance. The observations that reveal this weather are a testament to human ingenuity. By analysing the subtle changes in starlight during transits, we can detect the spectral signatures of these metals in both their gaseous and condensed forms. The way light is absorbed or scattered by the metallic clouds tells us about their composition and density. Observations of the planet's thermal emission, especially with the James Webb Space Telescope, allow us to map temperature variations across its surface, confirming the existence of those supersonic winds by showing how heat is distributed. Every new data point adds another piece to the puzzle, helping us understand the sheer violence and complexity of this world's atmosphere. In a broader sense, the extreme meteorology of this planet serves as a reminder of the incredible diversity of planetary environments. It shows us that the universe is capable of creating conditions that challenge our imagination and expand our understanding of physical laws. While this world is undoubtedly a hellscape, its furious weather provides invaluable insights into the forces that shape not only other worlds but the very fabric of cosmic evolution. So, as we continue to observe and analyze, we are not just learning about one planet's weather, we are decoding the universal language of atmosphere and energy, a language spoken in supersonic winds and metallic rains across the galaxy. Amidst the discussion of such unimaginable planetary weather, a fascinating and almost speculative question arises. Could this blazing giant of a world possibly host any moons? The idea of an exomoon orbiting this inferno seems like a contradiction in terms, a search for a snowball in a supernova. Yet it is a question that pushes the boundaries of our understanding of orbital stability and material science. The short and direct answer is that it seems incredibly unlikely for any traditional moon to survive here. The intense radiation and heat pouring from the star would make short work of any icy or rocky satellite we might be familiar with. A typical moon, even one as large as Jupiter's Ganymede, would be relentlessly baked. Its surface would heat to thousands of degrees, causing any ices to instantly vaporize and any rocky crust to melt and potentially even boil away. It would be unable to hold on to any semblance of an atmosphere, as the stellar wind and radiation pressure would strip it away almost immediately. The concept of a solid, differentiated world with a core, mantle, and crust simply doesn't hold up under such an onslaught. The moon would be reduced to a molten, featureless blob, dot, its geology dictated entirely by external heating rather than internal processes. However, this extreme environment leads scientists to speculate about even more exotic possibilities. What if a moon could not just survive, but adapt to these conditions? One hypothetical concept is that of a lava moon, a body that has fully embraced the heat. This would be a world with a surface that is entirely molten, a global ocean of magma constantly churned by the immense gravitational forces at play. It would have no solid crust to speak of, just a seething, incandescent sea of rock, potentially with a tenuous atmosphere of vaporized silicate materials. Such an object would be more of a coherent droplet of liquid rock held together by its own gravity than a traditional moon as we know it. The visual would be staggering. A glowing, orange-red companion orbiting the already blazing gas giant. A second-order inferno in a system of extremes. The gravitational environment for any potential moon would be incredibly complex and likely unstable. The planet itself exerts a powerful gravitational pull, but the nearby star's gravity is equally immense. This creates a fierce gravitational wrestling match over any smaller body in the vicinity. The stability of a moon's orbit so close to the star is highly questionable. The same tidal forces that lock the planet would act even more strongly on a smaller moon, potentially tearing it apart if it ventured inside the Roche limit. The point where gravitational tides overcome the moon's own structural integrity. Even if it avoided that fate, the gravitational perturbations from the star could easily destabilize its orbit over time, either sending it crashing into the planet or ejecting it from the system entirely. The tidal heating on such a moon would be monumental, far exceeding the volcanic activity we see on Jupiter's moon Io. The constant gravitational flexing from the nearby planet would pump enormous amounts of energy into the moon's interior, ensuring it remained a molten world even without the stellar radiation. This internal heating could drive spectacular volcanic activity, with eruptions orders of magnitude more powerful than anything in our solar system, spewing fountains of lava high into space. The search for such a moon is, for now, a monumental observational challenge. Detecting the faint, periodic dimming caused by a moon transiting its host planet is at the very edge of our current technological capabilities, even for planets in calm, temperate orbits. Doing so for a world orbiting a brilliant, active star dot, where the transit signals are tiny and incredibly fast, pushes the limits of what is possible. The moon's own light would be utterly drowned out by the combined glare of the star and the planet. Current methods are simply not sensitive enough to confirm or deny the existence of such a body in this particular system. However, the mere theoretical exercise is valuable. It forces us to consider the absolute limits of planetary science and the definition of a moon. Could a gravitationally bound sphere of liquid rock truly be considered a moon? How does the presence of a star so close change the dynamics of a planet-moon system? Exploring these questions helps refine our models of celestial mechanics and planetary formation in extreme environments. If a lava moon were ever discovered, it would represent an entirely new class of celestial object, expanding our catalogue of cosmic wonders and teaching us about the resilience and adaptability of matter under duress. It would also have implications for the planet's own history. The formation of a moon around a gas giant typically involves a giant impact early in the system's life or accretion from a circumplanetary disk. It is difficult to imagine how such a moon could have formed in situ given the violent environment, or how it could have been captured and retained its orbit during the planet's hypothesized migration inward. Its existence would therefore pose a whole new set of formation puzzles. For now, the question of an exomoon around this ultra-hot Jupiter remains in the realm of compelling speculation. It is a thought experiment that highlights the sheer violence of the system and the challenges of survival there. as our technology improves. With next-generation telescopes like the planned 30-meter telescope and the James Webb Space Telescope's continued mission, we may one day develop the techniques to probe these deepest mysteries. Until then, the image of a glowing lava world, a shimmering droplet of molten rock dancing around a gaseous titan in a binary embrace with a stellar furnace, remains a powerful testament to the imagination that drives astronomy and the endless possibilities that the universe holds, reminding us that sometimes the most valuable questions are those we cannot yet answer. While the very idea of life on this scorching world is laughable, its intense and hostile nature provides profoundly important lessons for the broader search for habitable worlds across the galaxy. This planet is the ultimate benchmark for uninhabitability, a place that defines the absolute upper limit of what we might call the conditions of planetary viability. By studying the processes that make this world so extreme, we gain crucial insights that actually sharpen our ability to find life on other, more temperate planets. The first and most direct lesson comes from understanding atmospheric escape. Here, we can observe in real time how a planet loses its atmosphere due to intense stellar radiation, particularly the high-energy ultraviolet and X-rays from a massive star. By quantifying the rate of this evaporation and modelling the physics behind it, scientists can better predict the fate of planets orbiting active red dwarf stars. Many of these stars are prone to powerful flares, and planets within their habitable zones are often close-in and potentially vulnerable to atmospheric stripping. This world serves as a natural laboratory showing us the worst-case scenario, helping us model how much atmosphere a planet can lose over time and still retain conditions suitable for life. Furthermore, the relentless photodissociation witnessed here, where powerful UV radiation tears molecules apart, is a key process to understand. It demonstrates that simply being in a star's habitable zone, where temperatures could allow liquid water, is not enough. The type of light the star emits is equally critical. A planet in the habitable zone of a volatile red dwarf might be subjected to radiation that systematically destroys the complex molecules necessary for life, even if the temperature is right. This planet shows us the destructive power of high-energy photons in action, teaching us that stellar activity is a major filter for habitability. Another crucial implication involves the interpretation of biosignatures. As we point our telescopes at distant worlds, we look for chemical imbalances in their atmospheres that could indicate biological activity. The classic examples are gases like oxygen, methane, DOT, or ozone. However, this ultra-hot Jupiter has taught us that many exotic chemical signatures have abiotic, geological, or photochemical origins. For instance, the detection of titanium oxide or other metal oxides in its spectrum is a purely physical phenomenon. If we were to see a similar, albeit weaker, signature in the atmosphere of a cooler planet, we might mistakenly interpret it. Studying this world's chemistry in extreme detail provides a reference library of what to expect from non-biological processes. It helps us avoid false positives by showing us the kinds of chemical signals that can be generated by sheer heat and radiation alone, without any need for life. This planet also dramatically illustrates the concept of the habitable zone as an incredibly narrow window. We often picture it as a broad, comfortable band, but the reality is far more constrained. This world shows us one edge of that window, the inner, blistering edge where a runaway greenhouse effect is not just about trapping heat, but about the complete molecular disintegration of an atmosphere. It underscores that habitability is a delicate balance of many factors: orbital distance, stellar type, planetary mass, DOT, magnetic field strength, and atmospheric composition. A small shift in any of these parameters can push a world from being potentially habitable to being a hellscape like this one. In this way, it deepens our appreciation for Earth's own stability and the rare confluence of conditions that allowed life to flourish here. Our planet has a protective magnetic field, a relatively quiet star, a robust atmosphere, and is situated at a comfortable distance. This ultra-hot Jupiter is the antithesis of all that, a reminder of how special and fragile a living world can be. The study of this extreme environment also pushes the development of our observational tools and theoretical models. The techniques used to analyse its evaporating atmosphere and exotic chemistry are the same ones that will be used to scrutinise the atmospheres of Earth-like planets. By testing these methods on a target that provides a strong dot, clear signal, we are calibrating our instruments and refining our algorithms. When we turn these refined tools toward fainter, more Earth-like worlds, we will be better prepared to interpret the subtle data they provide. Moreover, understanding the demographics of such extreme planets helps us place our solar system in context. How common are these ultra-hot Jupiters? Their prevalence tells us something about the frequency of planetary migration, a process that could potentially disrupt the formation of smaller, rocky planets in the habitable zone. If gas giants commonly migrate inward, they might scatter or consume any Earth-like worlds in their path, reducing the number of stable systems capable of hosting life. Therefore, finding and studying this planet isn't just about one world. It's about understanding the dynamics that shape entire planetary systems and their potential for hosting life. Finally, this world teaches a philosophical lesson about the diversity of planets. It expands our imagination and reinforces the idea that the universe is capable of creating a vast spectrum of worlds, most of which look nothing like the planets in our own solar system. This perspective is vital for a truly open-minded search for life. We must be prepared for the unexpected, but we must also be rigorous in distinguishing the merely bizarre from the potentially biological. This planet, in all its fiery glory, is a masterclass in that rigour. It shows us the boundaries, helps us refine our tools, and ultimately makes the search for another pale blue dot more focused and meaningful. It is a testament to the fact that even the most hostile and lifeless of worlds can provide the key insights that guide us toward finding one that is not. After exploring how this hellish world redefines the very limits of habitability, it is both humbling and enlightening to swing our perspective back to our own cosmic backyard and see how our familiar solar system planets stack up against this inferno. The comparison is not just an academic exercise. It is a stark reminder of the incredible moderation and tranquility we enjoy here, a perspective that makes our home seem almost miraculously placid. Let us start with Mercury, the innermost planet of our system. It orbits closer to the Sun than any other, and its day side can get incredibly hot, with maximum temperatures reaching around 430 degrees Celsius. That is certainly scorching, enough to melt lead. But when you place it next to the 4,000 degree plus environment of our ultra-hot Jupiter, Mercury seems almost frigid. In fact, the night side of Mercury plunges to hundreds of degrees below zero, a temperature swing that is dramatic but still within a range that allows for a solid, rocky surface to exist. There is no atmosphere to speak of, so no complex weather or metallic rains. Just a barren, cratered world that is a testament to the relative gentleness of our sun's output. Then there is Venus, often called Earth's evil twin due to its runaway greenhouse effect. The surface of Venus is a crushing, toxic environment with temperatures hovering around 460 degrees Celsius. Hot enough to easily melt many metals and sustain a surface pressure dozens of times that of Earth. It is a truly hostile place. But again, it pales in comparison. The entire climate of Venus, as extreme as it is for us, operates at a thermal energy level that is an order of magnitude lower than the day side of our benchmark planet. Venus has clouds of sulfuric acid and a thick carbon dioxide atmosphere, but it still has a solid surface where molecules can persist. On the ultra-hot Jupiter, the very concept of a solid surface is meaningless, and molecules are instantly obliterated. Venus, for all its fury, would feel almost hospitable next to that. Now, consider the gas giants in our system, Jupiter and Saturn. Jupiter is a massive world, a swirling tapestry of clouds and storms, most famously the Great Red Spot, a hurricane larger than Earth that has raged for centuries. The temperatures in Jupiter's upper clouds are bitterly cold, often dipping below -100 degrees Celsius. Its weather involves ammonia and water ice clouds, with lightning and powerful winds, but it is all happening in a relatively cold environment. There is no vaporized iron, no titanium rain, no supersonic global winds driven by a thousands of degrees temperature difference. Jupiter's atmosphere is complex and violent, but it is the violence of a cold, deep fluid dynamics, not the plasma physics of a star-proximal world. Even the hottest layers deep within Jupiter's interior are not remotely close to the stellar temperatures we are discussing. This comparison drives home a crucial point. Our solar system, for all its diversity and wonder, represents only a very narrow slice of the planetary pie. The models of planet formation and evolution that we built based on our 8 planets are just one example, one data point in a vast spectrum of possibilities. The discovery of worlds like this ultra-hot Jupiter forced a complete and necessary revision of those models. We had to incorporate new processes, like planetary migration, and new physical regimes, like atmospheric evaporation and photodissociation at stellar intensities. It showed us that our system is not the template. It is merely one possible outcome, and a rather calm and orderly one at that. This perspective is vital for the future of exoplanet science. It teaches us to expect the unexpected. When we look at other stars, we should not be surprised to find systems that look nothing like our own, with planets in orbits and configurations that defy our initial, solar system-centric intuition. This world, and others like it, are the outliers that stretch our definitions and force our science to grow. They demonstrate that a gas giant can exist so close to its star that it blurs the line between a planet and a brown dwarf star. They show that atmospheric chemistry can be dominated by atomic and ionic species rather than molecules. They prove that weather patterns can involve the condensation and precipitation of elements we normally consider solid in our solar system. The most extreme temperatures and pressures are found in the deep interiors of planets, hidden from view. On this ultra-hot Jupiter, those extreme conditions are right there on the surface, exposed to the vacuum of space and our telescopes. This accessibility is what makes it such a valuable laboratory. By comparing it to our own planets, we can ask deeper questions about the fundamentals of planetary science. What is the ultimate fate of a gas giant? In our system, Jupiter will likely remain a stable, cold world for billions of years. In this other system, the gas giant is on a short, dramatic timer, destined for destruction. How do magnetic fields behave? Jupiter has a powerful magnetosphere that shapes its space environment. Does this ultra-hot Jupiter have one? And if so, how does it interact with the stellar wind and magnetic field at such close range? The answers could inform our understanding of all magnetized planets. Furthermore, this comparative exercise highlights the rarity of Earth. Our planet sits in a delicate sweet spot, not too hot, not too cold, with a stable star and a protective magnetic field. Seeing the absolute extremes elsewhere makes us appreciate the intricate and fragile balance that allows life to thrive here. It is a perspective that is both sobering and inspiring. So, while we continue to discover and study these incredible, violent worlds at the edge of possibility, we should always remember to look back at our own solar system with renewed appreciation. It is our baseline, our reference point, but it is no longer the sole definition of what a planetary system can be. The cosmos is far more creative, diverse, and violent than we ever imagined, and that is what makes the journey of exploration so endlessly fascinating. Each new world we find, whether it is a temperate Earth-like planet or a blazing, ultra-hot Jupiter, adds another piece to the grand puzzle of how planets form, evolve, and interact with their stars. And in doing so, they help us understand our own place in the universe a little better. The quiet, ordered orbits of our solar system are just one melody in a cosmic symphony of incredible variety. And we are only just beginning to listen to all the different movements. Beyond being a fascinating curiosity or a mere record holder, this ultra-hot Jupiter and its kin serve a far greater purpose in the grand scientific endeavour. They are irreplaceable natural laboratories for testing the laws of physics under conditions so extreme they are impossible to recreate on Earth. This world is more than just a planet. It is a benchmark, a stress test for our theoretical models, and a catalyst for innovation in astrophysics. The value it provides is not just in the specific data we gather about its atmosphere, but in the universal principles we can derive and verify by studying it. Consider the field of atmospheric physics. On Earth, we study how gases behave under a relatively narrow range of temperatures and pressures. Here, we can observe an atmosphere pushed to its absolute limits. The behavior of various elements and molecules at temperatures rivaling those of stars is largely theoretical. This planet allows us to test the opacity of these materials, that is, period. How effectively they absorb and emit light at different wavelengths under stellar-level heat. The data we get from its transmission and emission spectra directly validates or refines the complex models used to understand not just planetary atmospheres, but also the outer layers of stars themselves. The processes of evaporation and photodissociation observed here are not unique to this world. They are fundamental interactions between radiation and matter. By quantifying the rate at which the star's UV radiation strips away the planet's atmosphere, we gain crucial insights into the early evolution of planetary systems. Young stars are often far more active and violent than their older counterparts, bathing their nascent planets in intense radiation. Studying this extreme example helps us model the atmospheric escape that likely shaped the destiny of many young planets, including those in our own solar system billions of years ago. It answers questions about how a planet's initial atmosphere is eroded and transformed, which is a critical step in understanding the pathway to habitability for rocky worlds. The planet also serves as a supreme test for fluid dynamics. The supersonic winds and global heat redistribution present a computational challenge of the highest order. Simulating the flow of gas at thousands of kilometers per hour across a planet with a temperature difference of thousands of degrees between its hemispheres pushes our most powerful supercomputers to their limits. The models that succeed in replicating the observed conditions on this world become more robust and reliable. These refined models can then be applied to a wider range of problems, from predicting the weather on other exoplanets to understanding the atmospheric circulation of brown dwarfs, and even improving climate models for Earth by exploring dynamics in a completely different regime. Furthermore, the exotic chemistry we detect acts as a rigorous proving ground for thermodynamic equilibrium calculations. Predicting which molecules and atoms can exist at these temperatures, and in what quantities, is a complex task. The detection of specific high-temperature species like titanium oxide or ionized iron provides a direct check on these theoretical predictions. Each confirmed detection boosts our confidence in the underlying physics, while each unexpected absence or presence forces a re-evaluation and improvement of the models. This iterative process of prediction, observation, and refinement is the very engine of scientific progress. The planet's extreme gravity and proximity to its star also make it a perfect site for studying tidal interactions. The theories of how tidal forces flex a planet's interior, generate heat, and cause orbital decay are put to the test here. By meticulously monitoring the planet's orbit for tiny changes in its period, astronomers can measure the rate of tidal decay directly, providing hard data to constrain models that describe the internal structure of both the planet and the star. This has implications for understanding the long-term stability of many compact planetary systems, including those with potentially habitable worlds. The magnetic interactions, if they can be detected, would open a window into magnetohydrodynamics in a regime where the magnetic and plasma pressures are comparable to the thermal pressure. The potential for star-planet magnetic coupling, leading to powerful auroral phenomena and additional heating, is a frontier of plasma physics that we can observe on a planetary scale. This is knowledge that cannot be gained in any terrestrial lab. In essence, this world is a bridge between planetary science and stellar astrophysics. It possesses qualities of both, allowing us to study stellar-like conditions in a planetary context. The data we gather from it helps calibrate our understanding of stellar atmospheres and the behavior of matter in high-energy environments. Every new observation, especially from telescopes like JWST, is the experiment that tests our theoretical framework. A successful prediction validates our models. A surprise finding reveals a gap in our understanding and guides future research. This constant feedback loop is what drives astrophysics forward. Therefore, the importance of this planet transcends its own bizarre nature. It is a cornerstone for fundamental physics, a tool for refining our simulations, and a reminder that the universe itself provides the most rigorous laboratories. By studying this ultimate inferno, we are not just learning about one world. We are stress testing the very theories that describe how matter and energy behave across the cosmos. The insights gained here ripple through the entire field, improving our models, sharpening our predictions, and ultimately deepening our comprehension of the physical universe. From the smallest atomic interaction to the largest cosmic structures, it is a testament to the fact that sometimes, to understand the ordinary, we must first comprehend the extraordinary. The incredible insights we have gathered about this scorching world, from its evaporating atmosphere to its metallic rains, would be nothing more than a theoretical fantasy without the monumental technological advancements of the past few decades. The detection and detailed characterization of this planet represent a pinnacle of human engineering, a symphony of optics, detectors, and computing power working in perfect harmony across millions of kilometers of space. It all begins with the telescopes themselves. The initial discovery often comes from ground-based, automated, wide-field survey telescopes, like the Kilodegree Extremely Little Telescope Network that gave this class of planets its name. These are not the giant, iconic domes you might picture. They are relatively small, robotic instruments designed to do one thing incredibly well: continuously monitor large swaths of the sky, measuring the brightness of thousands of stars night after night. Their purpose is to find those tiny, periodic dips in starlight that signal a transit, This requires phenomenal photometric precision, the ability to detect a change in brightness of less than 1%, often buried within the noise of Earth's turbulent atmosphere. Finding this particular planet was like spotting a single, specific grain of sand on a vast, constantly shifting beach, and it was these dedicated survey missions that first noticed the subtle, repeating pattern. But discovery is just the first step. Confirmation and, more importantly, understanding the planet's mass came from another technological marvel: high-resolution spectrographs. Instruments like HARPS in Chile and its more advanced successor, ESPRESSO, are masters of precision. They are designed to measure the Doppler wobble of a star, the tiny back-and-forth motion induced by an orbiting planet's gravity, to detect the wobble caused by this planet. These spectrographs must be stable enough to measure changes in the star's radial velocity with a precision of meters per second or better. This is akin to measuring the speed of a crawling baby from light years away. They achieve this by using a frequency cone, a laser source that creates an incredibly stable ruler of reference lines against which the star's spectrum is compared. Any shift in the star's spectral lines, no matter how minute, is detected, allowing us to weigh the planet. The next leap in understanding came from moving above Earth's obscuring atmosphere. Space telescopes have been utterly transformative. The Hubble Space Telescope, with its stable platform above atmospheric distortion, provided some of the first reliable data on the composition of exoplanet atmospheres through transmission spectroscopy. Its ability to observe in the ultraviolet was crucial for studying the atmospheric escape and the dramatic tales of these ultra-hot worlds. The Spitzer Space Telescope, though now decommissioned, was an infrared pioneer. It gave us our first real measurements of the heat emanating from the day sides of exoplanets, allowing us to map their energy budgets and understand their temperature extremes. But the current game changer, the instrument that has pushed this field into a new era, is the James Webb Space Telescope. JWST is an engineering marvel on every level. Its 6.5-meter primary mirror, composed of 18 gold-coated beryllium segments, collects an enormous amount of infrared light. Its location at the second Lagrange point provides a stable, ultra-cold environment, essential for its infrared sensors, the key instruments for exoplanet science. NIR SPEC and MIRI are miracles of miniaturization and sensitivity. NIRSpec can observe hundreds of objects simultaneously, while MIRI probes deeper into the infrared, all while being cooled to temperatures only a few tens of degrees above absolute zero to suppress its own infrared glow. The data from JWST is of such high quality that it is like moving from a blurry, pixelated black and white photo to a crisp, high-resolution colour image. It can detect the specific infrared fingerprints of individual molecules in a planet's atmosphere, measure temperature variations across its surface, and peer deeper into the atmospheric structure than ever before. However, these advanced observatories are only part of the story. The raw data they send back is not a ready-made scientific paper. It is a complex digital signal filled with noise and systematic errors. This is where the final crucial piece of technology comes in: the supercomputer and the algorithm. Processing the data from a single transit observation with JWST can involve terabytes of information. Scientists use sophisticated algorithms to clean the data, correct for instrumental effects like cosmic ray hits and pixel-to-pixel variations, and model the subtle astrophysical signals. They must account for the star's own activity, its spots and flares, which can mimic or obscure planetary signals. Extracting a clear transmission spectrum from the noise requires complex statistical models and machine learning techniques, all running on powerful computing clusters. The physical models used to interpret the spectra are themselves technological achievements, incorporating quantum mechanics, atmospheric chemistry, and fluid dynamics to simulate conditions we can never visit. This entire pipeline, from the robotic telescope on a mountaintop to the space-based observatory to the supercomputer in a lab, represents a global, collaborative effort. It is a testament to human curiosity and ingenuity that we can build machines that not only find a distant world but also tell us what it is made of, how hot it is, and how it is slowly being destroyed by its star. This technological journey is far from over. Future missions like the ESA's PLATO will launch with even more advanced cameras to find thousands more planets, while ground-based giants like the extremely large telescope will use adaptive optics and advanced coronagraphs to try and directly image the faint glow of planets like this one, separating their light from the blinding glare of their stars. Each new tool builds upon the last, expanding our vision and deepening our understanding of the cosmos. So, when we marvel at the discovery of an iron-raining, supersonic wind-swept world, we are also marveling at the telescopes, the spectrographs, the space probes, and the algorithms that made it possible. It is an achievement that stands on the shoulders of engineers, programmers, and scientists who turned the dream of studying distant worlds into a breathtaking, data-rich reality. The story of this planet is, in equal measure, a story about the universe and a story about us, about our relentless drive to build better tools to see further and understand more. Despite the incredible technological prowess that has allowed us to peer into the heart of this blazing world, uncovering its secrets of evaporation and metallic storms, the story is far from over. In many ways, the more we learn, the more we realize how much we still have to discover. And this unknown frontier is what fuels the next generation of astronomers and engineers. The current picture, while detailed, is still frustratingly incomplete. For instance, the planet's internal structure remains a total mystery, completely hidden beneath its opaque, turbulent, and violently churning atmosphere. We have a good estimate of its mass and size, which tells us it is a low-density gas giant, but what lies deep within its core is pure speculation. Does it possess a solid dot, rocky core at its centre, a remnant of its initial formation, or has the intense heat and pressure completely dissolved any such structure into a more homogeneous fluid state? Understanding this is crucial because the core's existence and composition would reveal vital clues about how the planet formed and migrated to its current orbit. And it would influence our models of its magnetic field and internal heat dynamics. Speaking of magnetic fields, this is another massive question mark. The nature and strength of this planet's magnetic field, if it even has one, are subjects of intense speculation and complex computer modelling. The host star undoubtedly has a powerful magnetic field, and the interactions between the two could be dramatic, potentially generating those immense auroras and contributing to atmospheric heating. But without direct detection, we are left with hypotheses. Does the planet's rapid rotation and internal convection generate a dynamo effect, creating a strong magnetic field that helps deflect the stellar wind and shape its evaporating tail? Or is the field weak or non-existent, leaving the atmosphere fully exposed to the stellar onslaught? Answering this would not only tell us about this specific world, but also refine our understanding of magnetic field generation in gas giants under extreme duress. Beyond these big mysteries, there are countless finer details we are missing. The precise mechanisms driving the supersonic winds are modelled but not directly observed. We infer their existence from temperature maps. How do these winds interact with the planet's rotation and the gravitational tides from the star? The chemistry, while we have detected several elements, is likely even more complex. Are there other, rarer elements or short-lived molecules forming in the turbulent interface between the day and night sides that our current instruments cannot see? The continuous evaporation process itself has nuances we do not fully grasp. Is the mass loss constant, or does it spike during periods of heightened stellar activity? These unanswered questions are not dead ends. They are the launch pads for future exploration. The next chapter in this saga will be written by a new fleet of missions and telescopes designed to probe deeper than ever before. The European Space Agency's PLATO mission, for example, is not specifically targeting this planet, but its primary goal is to find and characterize thousands of exoplanets around bright stars. By discovering more ultra-hot Jupiters, Plato will help establish robust statistics. Is this planet a rare fluke, or is it a common outcome in the evolution of planetary systems around massive stars? Understanding its prevalence will tell us how often such violent migration and evolution occur, shaping our overall view of planetary system architecture. Meanwhile, the next generation of ground-based telescopes is preparing to attempt the seemingly impossible: direct imaging. The extremely large telescope, with its mirror measuring 39 meters across, is being built with this exact challenge in mind, using advanced adaptive optics and sophisticated coronagraphs to block the overwhelming glare of the host star. The ELT will try to capture the faint, pinpoint glow of the planet itself. Success would be revolutionary. It would allow us to study the planet independent of its transits, potentially measuring its colour, mapping its cloud patterns in reflected light, and even analysing its rotation directly. We could watch as it orbits, seeing the contrast between its day and night sides, not just through inferred temperatures, but potentially through actual images, albeit crude ones. This would open a whole new window into its atmospheric dynamics. The James Webb Space Telescope is already providing breathtaking data, but its mission is ongoing, and future observing cycles will undoubtedly target this world with even more sophisticated observing strategies. Other proposed missions, like the Habitable Worlds Observatory or advanced space-based interferometers, could further enhance our ability to characterize such extreme environments. The technological innovation required for these endeavors is driving progress in optics, detector sensitivity, DOT, and data processing algorithms. The journey to understand this infernal world is a perpetual cycle of discovery. Each new answer, each piece of data from a powerful telescope, does not close a book. It opens a new one, revealing deeper and more profound questions. Solving the mystery of the internal structure might lead us to wonder about the composition of that core. Confirming the magnetic field would prompt inquiries into its strength and its role in atmospheric retention. Directly imaging the planet could reveal unexpected surface features or weather patterns that challenge our current models. This iterative process is the very engine of science. It motivates students, inspires engineers, and captivates the public. It reminds us that exploration is not a destination, but a continuous path. The study of this single, extreme world is more than just an academic pursuit. It is a benchmark for our capabilities and a guide for our future. It teaches us humility, showing us the limits of our current knowledge, and it fuels our ambition, pushing us to build better tools and ask sharper questions. As we stand on the brink of these new technological frontiers, one thing is certain: the story of this ultra-hot Jupiter is still being written. The next chapter promises to be even more exciting than the last, filled with new revelations, unexpected twists, and a deeper appreciation for the violent and beautiful complexity of our universe. The unanswered questions are not a failure of our science, they are its greatest promise, ensuring that the wonder of discovery will continue to drive us forward for generations to come.